Hello again everyone, welcome back to ptet.chemistry channel. So in this restructured format of the tutorials, I will not show question paper. Instead what I'll tell you is 9701. So it's an A-level chemistry paper. This is for the June 2021 or the summer 21 session. This is a paper 4. Variant 1, so it's a full A-level paper, which is why it's one of the longer paper, and the duration of this tutorial for paper 4 is usually exceeding 3 hours to 3 hours and a half, and that's typical because I talk on concepts that are related to the question as well, but I'll try to move on as soon as I can, but not at the expense of going through questions and thinking about the underlying concepts and the associated concepts that I think are important on answering the question. Before I start, there's a button on the bottom right to all the videos on the channel, so don't forget to click the button to subscribe to the channel, and turn on notifications so that you get notified of all the latest videos. Follow me at ptet.chemistry, that is at ptet.chemistry on Instagram, Facebook and Twitter to get connected, and please share the channel widely with all your friends, chat group, juniors, seniors, teachers, relatives and whoever else you think the channel might be useful for. So do help them by sharing the channel widely. Let's get started. In this question 1, we have a group 2 chemistry. This is a 3-mark essay question. Essay in the sense that you can actually prepare for it. This is slightly different. This is about thermal stability. So usually when they talk about thermal stability, they talk about thermal stability of group 2 carbonate as well as group 2 nitrate. Those are in the syllabus. But this one is group 2 hydroxide, so M2 plus, M2 plus and OH minus, so you do actually need 2 of the OH minus to balance out the charge from 1 of the M2 plus. What they've told you is this thermal stability is similar to the thermal stability or similar to that of group 2 carbonate. So I know about the group 2 carbonate because that is expected in the syllabus. So what I can say is I can explain first. Down group 2, there are more field in a shell. So if there are more field in a shell, what we can say is that the size, the ionic radius of the M2 plus cations would increase, and when that increases but the charge remains plus 2. So what happened is the charge density. So charge density of M2 plus will decreases because charge density is charge over size, charge over volume. Your charge is the same, but your size get bigger and bigger due to more shells being filled. Therefore, your charge density decreases. Your M2 plus becomes less polarizing. Your cation polarizes the anion, so they become less polarizing on the anion, which in this case is hydroxide, because this question is specifically asking you on the hydroxide. Okay, therefore the OH covalent bond is less weakened due to it being less polarized. Okay, if that is true, therefore the MOH twice, meaning the group 2 hydroxide, become more difficult to break down, more difficult to decompose. They're asking you on thermal stability, so I've started by explaining first, but now I will state the thermal stability. So if they become more difficult to decompose, therefore the thermal stability increases because they become more stable to heat, they become more difficult to decompose down group 2. So the thermal stability group 2 hydroxide increases there. Question 1, part B, you have KSP. So the second part is asking you on KSP. The first part is asking you on the dissociation of the calcium hydroxide as a solid. They said dissociation of these as a solid in aqueous solution. So if I plus aqueous, meaning in a large amount of water, it's reversible because not a lot of it is soluble, only some of it are soluble. Hence we are talking about KSP there. They want you to include that symbols because there's the idea about KSP that a sparingly soluble solid dissolved in a large amount of water, only a certain amount goes into the solution. So these are aqueous and aqueous. In terms of stoichiometry and balance equation, they need to follow the formula of that calcium hydroxide. You got has that symbol because the question asks for it. In part 2, they are asked to calculate the solubility. So if I want to calculate solubility, I need to think about what solubility actually means. The unit of solubility there is mole per dm cube. That means how many mole of these dissolve in 1 dm cube of water. So if the solubility, meaning how many mole of calcium hydroxide dissolve in 1 mole, or how many mole of these dissolve in 1 dm cube of water, if x mole per dm cube, that would mean that, oops, they don't use per dm cube, they use dm minus 3. So clearly I've been teaching year 9 chemistry for too long. Anyway, so if I have 1 mole of these that dissolve, I'll get 1 mole and 2 mole of these. If I get x mole that dissolve in 1 dm cube of water, therefore I'll get x times 1, because 1 mole give me 1 mole, x mole in 1 dm cube give me x mole in 1 dm cube. And this one, 1 mole of these give me 2 mole of these. So x mole of these dissolve in 1 dm cube to give me 2x mole of hydroxide. So ultimately, so Ksp is equal to the calcium 2 plus concentration to the power of 1, because the number in front of the balance equation is 1, multiplied by the OH minus square, because the power in front of the power to which you rest the concentration is the stoichiometric number in front of the balance equation. So what happened there is, I think it's best if I actually move this to a new page, because I think instead of saving up the space, it's better we fill up the space there. So what happened then is the solubility product is written in such expression. I just need to put in the value. So the calcium 2 plus has a concentration of x, OH minus is 2x. Don't forget, the square is for the whole thing in the bracket. So a lot of students forget that it's the 2x, the whole thing square. They just write down 2x square, which is incorrect. I'll just write down Ksp first without putting in any value. So that will give me 4x cubed. So x cubed equal to Ksp over 4. So I can get x equal to the cube root of Ksp over 4. Now I am ready to put in the value. So there is 5.02 times 10 to the power minus 6 divided by 4. And there's the cube root. So press down to your calculator. Divided by 4, I get 1.255 to the power of minus 6. Don't forget to cube root that thing. And I would have gotten 0.0107865. I don't need that many significant figure. Looking at the data they have given us for Ksp, 1, 2, and 3 significant figure. So back in AS under the first topic in calculations, they say candidates should be able to appreciate what is appropriate number of significant figure based on the data given. This is 1, 2, and 3 significant figure based on the data given. So I will run this up to 3 significant figures. So I look at the fourth one, which is more than 5. So that's 108 mole per dm cube. This is how much of the calcium 2 plus ion dissolve in 1 dm cube of water. And this happens to be the same concentration of these. So the solubility is going to be the concentration of calcium hydroxide, which is X. So we're looking at the answer. Solubility, well, let's say calculate whatever. So the solubility is equal to 0.0108 mole per dm cube as your final answer there, which is going to be how much of these dissolve in 1 dm cube of water, happen to just be X there as well. Part 3, so it's quite a straightforward question, so I'll probably just do it on this page. We're thinking about how it would vary compared to solubility in aqueous sodium hydroxide. So what happened then is we are looking at this equilibrium. If I just very quickly show you again. So you have this equilibrium, which is due to that calcium hydroxide not being very soluble. But then you also have NaOH, which is completely soluble. So what happened then is when you have aqueous sodium hydroxide compared to just in water you don't have this extra OH minus contribution. So what happened then is in the presence of OH, or in the presence of aqueous sodium hydroxide, there are more OH minus. So there are more OH minus ions in the equilibrium. So together, they're existing together, because the amount of OH minus from here is full dissociation, is going to far exceed the amount of hydroxide from there. And because now you have more hydroxide in the equilibrium, what will this system do in response to the increase in OH minus concentration? So OH minus concentration increases. What will equilibrium do? That is to do with Le Chatelier principle. Therefore, the KSP equilibrium will try to decrease. It will try to decrease OH minus concentration by reacting more OH minus. So it will shift to the left side. When you shift to the left side, you are making it becoming less soluble. So you will precipitate out the solid, because as you go from left to right, you're making it more soluble. So as you shift to the left, you will get more of the solid. Therefore, more of the calcium hydroxide will precipitate out, meaning to say you will get more of the solid coming out. So therefore, solubility of calcium hydroxide decreases. They say suggest how it would vary compared to in water. In water, you don't have these, so the solubility of calcium hydroxide in aqueous sodium hydroxide would decrease, will be lower. In aqueous NaOH is lower, or the solubility decreases. Okay, so I think that is the key to that question, really to think about the Le Chatelier principle in terms of more OH minus ions as a result of full dissociation. Because it's a strong base, it dissociates completely. What happened to the OH minus concentration? What would the KSP try to do? It will try to decrease it in response to the change in the system. So that's the end of that 7-mark question there. Moving on to question 2. So this question 2 starts off on the origin of color, or origin of color in transition metal complexes. So this question would have been familiar to many students trying to prepare for the A-level 9701, or in fact any other 16 to 18 years old chemistry exams. It's all about this origin of color, or why are transition metal complexes colored. In this particular question, chromium complexes are colored because, well, chromium belong to transition metals, because chromium has a partially filled d orbitals. Okay, so first of all, I think in the context of this question, I will say that chromium has a partially filled d orbitals. Has a partially filled d orbitals in most of its ions. When forming complexes or when forming compounds. When forming complexes, or compounds. So this is just an additional point which I don't usually add onto my fixed essay, but I think it's quite relevant in the context that, you know, we are saying that there is a partially filled d orbital which are occupied, has a partially filled d orbital with the d electrons in most of the ions, and in most of the ions when they form complexes or the compounds. Let's get started with the main essay. So we know that we have the degenerate d orbitals. So I would probably draw this as some stage on the side, and I know they will be split into 2 energy levels in the presence of ligands. So this is Ml6 complex when it is octahedral, and this is just metal atom, no ligand. Okay, so in the context of chromium atom, it's got partially filled d orbital. When they form complexes in most of the ions, it will have partially filled d orbital as well. So both of them are rare sum in energy because of the repulsion that the ligands bring electrons with it, and the active covalent bond to the metal atom that has got electrons in the d orbitals. So the repulsion causes the energy levels to go up in energy by a certain amount. I've seen in books as well, and I've done it in the past as well, where I don't show them going up, I just show them splitting like that. It's entirely acceptable as well, because everything is relative as long as this is being split and they're no longer equal in energy, as the electrons in these orbitals repel differently to the electrons in this orbital with the incoming ligand. And this energy gap is characterized by delta, meaning difference in energy, equal to Planck constant times frequency of the radiation, which is going to be visible light radiation. So it's going to be hc over lambda absorbed, because, well, electromagnetic wave, which visible light belongs to, they travel at the speed of light, so c equal to f lambda. Anyway, so in terms of putting it into words, what can we say? We can say that the degenerate in the presence of ligands, or when ligands are present, then the previously degenerate d orbitals. Degenerate mean the same energy. So the previously degenerate d orbitals get split into two sets of energy levels. Two sets of energy levels, 3 at the bottom, 2 on the top, 4 octahedral complex. This is an octahedral complex, ML6, 2 sets of energy levels. So what can happen then is the electrons, oops, I haven't mentioned about the energy gap yet. These energy levels are separated. These energy levels are separated by the energy gap. Delta E is equal to HF equal to HC over lambda absorb. Okay, so the electrons in the lower energy level can get promoted, or they can get excited. So promoted or excited to the higher energy level by absorbing visible light. So visible light refers to those light photons in the visible light region. By absorbing visible light, and you cannot occupy all those empty space in between. The electrons can only sit in orbitals, so they have to absorb a specific wavelength that corresponds to this energy gap as characterized by this equation. This is Planck constant, this is frequency of the radiation, this is speed of light, this is the lambda, meaning the wavelength of the visible light being absorbed. So what color do we see? The color of complexes seen will be complementary. The color of complexes seen or observed is complementary. So there's a color wheel associated with this, actually complementary to that being absorbed by the complex. So whatever is being absorbed does not pass through. So whatever you see is a result, or is a combination of whatever that passes through. Okay, so that's basically the fixed essay on these kind of questions. Typically speaking, we'll just start our essay from here and then just end here without this thing. I'm pretty sure if you don't fill this in, you will still get all the marks, because there are more than enough points in here that usually justify for why you get colors in transition method complexes, or the origin of color in transition method complexes there. Okay. Moving on to question 2, part B. So this looks like coordination chemistry. So this is very similar to one of the question that has appeared in previous papers. So what do we have? We have CrCl3 and then H2O6. We have CrCl3 and H2O5. CrCl3, H2O4. So it seems they are decreasing in that order. So there are more and more water molecules in there. And this is the mole of AgCl precipitated out per mole of complex. This is important information. In 1 mole of complex, how many mole of AgCl does it give off? Give off 3, give off 2, give off 1 and 1. So this is what you label P, Q, R, and S. And then in terms of the shape, not shape, but is it polar or non-polar? I don't want to exactly copy down the question, because again, there's a copyright issue. And again, well, you know where to find the paper yourself. I am not telling you where to find the paper. I am simply going through the tutorial as if you know where to find this particular paper. So what we can see is you give off 3 AgCl, because what does this information tell you? That means there are 3 free Cl minus, there are 2 free Cl minus. Free in the sense that, you know, they are not coordinated. If they are not coordinated, that means they will precipitate out the AgCl. But if the Cl minus is bonded, or dative covalent bond, to the metal ion center, to the chromium center, that means they are not free. Okay, so the fact that they are free there would imply that, the chromium has just got a H2O ligand. Out of the 3 Cl, only 2 are free. That means you've got 1 chloride on the chromium, which makes sense because 1 chloride is 1 monodentate, and you got 5 of the monodentate water. So altogether, you still have octahedral complex with 6 dative covalent bond, but 1 of the chlorine. So in the complex, complex would be 1 times Cl minus and 5 times H2O. As a result of this information given, because there's 1 chloride, they are coordinated, whereas there is only 6 times H2O coordinated in the complex there. And there's 1 free chloride, so I have got 2 times Cl minus coordinated to the chlorine, and I have H2O times 4. So that is true for that. And these are the same scenario, so I can say they are the same. But what is different is one is polar and one is non-polar. As you can imagine, these are all octahedral complexes. Octahedral complexes they have bond angle of 90 degrees to each other. The fact that this is non-polar means that dipoles cancel out. As you can imagine, there is a symmetry. So we are looking at symmetry. And we have 2 times Cl minus and 4 times H2O. So you can imagine the 2 times Cl minus 180 degrees to each other. That's why they cancel out, and the 4 water is square planar in the middle of the plane. Let's get started with this question. So B part 1. Draw the 3-dimensional structure for P, Q, R, and S. So I already started by talking about the origin of why I know there are 6 water molecules. They want the complex ions. They don't want the free chloride or whatever. So they just want the complex ion. So if you have 3 free chloride, each of which is minus 1, and 3 times minus 1 is minus 3, this means this charge there is going to be plus 3 on the complex because the water has no charge whatsoever. If you got 2 free chloride, this is minus 1 times 2 is minus 2. So altogether, this complex remaining that has got 1 chloride and 5 water is going to be plus 2 overall. So that I'm talking about the charge on the complex. So be careful there. So I just want to highlight that very early on. So perhaps I can show P. So chromium there. So they haven't shown you the 3-dimensional thing at all. So I need to show these lines where these 2 are flat. These 2 are coming out towards you, coming out from the screen, from the paper. These 2 are away from you, behind the screen, behind the paper. So you can't draw them as just line because they are not flat at all. If I just copy these very quickly, because I don't want to have to draw them again and again. And they have given us R and S at the bottom as well. So R and S. Okay, so that's P, Q, R, and S. So remember what I said about P earlier? So 3 times free chloride, that means all the chloride are free. So there's 6 water around the complex. So we're looking at P being chromium, H2O6. So this is chromium 3 plus because you got 3 free chloride, each of which is minus 1. So I have OH2. OH2, remember, is the lone pair on the oxygen. The lone pair on the oxygen is the one with the electrons or the lone pair in order to form dative covalent bond. So do not show your arrow going to the space in between or to the hydrogen because the lone pair is on the oxygen to form that dative covalent bond. In Q, you have 2 free chlorides, so you have 1 chloride and 5 water on the complex. So you have 1 chloride and 5 water on the complex. So you still have 3 plus on the chromium, but you got minus 1, so overall it's 2 plus. That's why there's Cl minus and Cl minus. That's why there's 2 free chloride. That's why you get 2 mole of AgCl for 1 mole of this complex because there are 2 free chloride. So I just have 1 chloride which I can put anywhere. I'm just going to put my chloride on the axial rather than the equatorial. It doesn't matter whatsoever. What is important is I need to try and get the charges right. So, I try to put in my charges on my complex all the time. What I can do now is I can draw for R and S. But R and S, similar concept, 1 free chloride means 2 of the chlorides are coordinating on the chromium. And I have 4 water, but one of them is polar and one of them is non-polar. I said earlier the dipoles cancel out for S because the chloride are 180 degrees to each other. So I can draw S first, where the dipoles cancel out. So the chloride are 180 degree to each other. So CrCl2, H2O4, and that will be a plus now because plus 3, minus 1, leaving me 2 of the chloride. And then we fill the rest with the water. So remember, it's the oxygen with the dipole, sorry, no, it's the oxygen with the lone pair that will form dative covalent bond to this complex center. So we've got an overall charge of +1 there, and that will cancel out the dipoles because this dipole of the chloride both are axial, so these cancel that, these cancel that, and these cancel that. So everything will lead you to this complex being non-polar. So this is what you call a trans, because the chloride and the chloride are 180 degree to each other, whereas here the chloride and the chloride are 90 degree to each other. As you know, the bond angle in the octahedral geometry is all 90 degree, including in the square planar equatorial position. They're all 90 degree to each other, even though I've drawn this bit at the back a bit bigger, but they're all supposed to be 90 degree square planar in the middle. But then these things are linear, so together you got 6 bond pair and 0 lone pair, octahedral 90 degree. So here I could have put the chloride anyway, as long as the Cl and Cl are 90 degree to each other, and I fill in the rest of the ligand space with just the monodentate water. I will also have a +1 complex again, because this is also chromium with 2 chloride, because I only have 1 free chloride, because I only precipitated out 1 AgCl per the complex. I only give out 1 AgCl. That means 2 of my chloride are not free. They are bound onto the chromium. But this R is polar because the dipoles do not cancel each other out. So this is a polar complex. Whereas the one on the right hand side, complex S, the dipoles does get cancelled out. So that is the non-polar complex. This is cis, the other one is trans. So the trans one is the non-polar complex. So I hope that is quite clear there. Not too sure if I can make it a bit clearer. Perhaps I can draw a partition there. That seems better. Perhaps I can draw a partition there. That seems better. So it looks a bit neater because there are boxes in the question. They do say that draw 3-dimensional diagram. So 2 out, 2 in, and 2 are flat. Include the charges for each complex ion. I included the charge already because there are 3 free chloride. Based on this information, there are 2 free chloride. So, you know, 1 is bound. So +3 minus 1 give you +2. +3 minus 1 minus 1 give you +1 for the charges that I have included there. So on to the next question. So question 2b, part 2, they say why S is non-polar. So I already mentioned it just now. S was the last one there because the chloride ligands, the chlorine and the chlorine there, are 180 degree to each other, because the two chloride ligands, the 2 Cl minus ligands, are positioned trans, meaning 180 degree to each other. Therefore dipole cancel out. Therefore symmetrical, so it has a symmetrical structure. As a result of the symmetry, their dipoles cancel out. When dipole cancel out, no overall dipole. Therefore, no overall dipole. It's a 1-mark question. I guess you can probably skip to the point and just take the most important information. They give us 2 lines. I've written more than 2 lines. The idea is about the trans geometry, symmetrical structure. The dipoles cancel out. That's why this molecule is non-polar. So this cancel that cancel that cancel that. Question 2, part C, this is about definition. So they want you to talk about this picolinic acid. So let me try and get that right first. That, and I have CO2H. So they call this picolinic acid. They say the conjugate base is a bidentate ligand. So this is a carboxylic acid. So when you deprotonate that, then it's a carboxylic acid, so it's going to be a weak acid, so it partially dissociates into the H+ ion. When it does that, then you will be left with something called carboxylate, something that look like this. This is a carboxylate. This is the conjugate base, And what they are saying is the conjugate base can be a bidentate ligand. Originally, we have a lone pair on the nitrogen there, and now we also have a lone pair on the oxygen that we can see there. So altogether, you have two sites, one like this and one like that, as your possible coordination site. So one molecule or one ion or one such species can form two dative covalent bonds to the transition metal or the metal ion center. So what is the definition of bidentate ligand? So there are two parts to this definition. What is bidentate and what is ligands? So bidentate ligand forms two dative covalent bonds. So very important. So two dative covalent bonds to metal ion or metal center per ligand molecule or per ligand ion. Per ligand ion. Okay, so this is an ion. So in one of these ions, it forms two dative covalent bonds per one single ion. So it's very important to mention that for one single ion, they form two dative covalent bonds. They have at least two species with two individual lone pairs. They can form two dative covalent bonds. If I were the examiner, I'll be looking at two dative covalent bonds. I'll be looking at per ligand molecule or per ligand ion, because it means in one ligand, how many dative covalent bonds do you form? Here, I've just shown you that. They are not asking you to do that. Are they? Yes, they are. They do ask you to show the structure of Z. So, you know, this kind of thing, they always follow one another. You do not need to show the dative covalent bond because they just want you to show the structure of Z. So that is Z, which is the conjugate base. Conjugate base is what you get after the acid donates the proton. After the acid donates the proton, you get something called conjugate base. That's in your AS equilibrium under acid and bases. Okay, so what do we have? Z reacts with aqueous chromium 3 plus in a 3:1 ratio. Okay, so this is about coordination chemistry. So if I have Z, I have 3 of Z because it's a bidentate ligand. So 3 of Z plus what? Plus chromium H2O 6, 3 plus. So I will have 1 of these and I'll have 3 of that. And what I will get is I will expect to get chromium Z, 3 of Z. Each of Z has a -1 net charge. So if I have 3 of that, I will have, originally I have +3 charge because the water has 0 charge. So that's why overall is +3 oxidation state. So the chromium is still +3, but each of the Z is -1. So each of the Z is actually -1. But I have 3 of Z. So altogether, I have +3, cancel out -3, I will have 0 charge. Okay, so no charge at all. So I don't show the charge. Coordination number, oops, I don't mean to do that. So remember, this is bidentate. Bidentate means two dative bond per ligand. So I have 3 of the bidentate. So 3 bidentate would mean 6 dative bonds. I am really running out of space here, so what I'll do is I will copy all of these onto a new page so that I will not be hesitant to use more space if I have to. So 3 bidentate ligand would mean 6 dative covalent bond. 6 dative bond would mean coordination number is going to be 6. Okay, because coordination number is defined as the total number of dative bonds, dative covalent bonds around the metal ion in the complex. You have 6 dative covalent bonds, even though you only have 3 bidentate ligands. Your geometry is going to be octahedral because they are still 16 around the complex. Okay, so octahedral complex, octahedral geometry, 6 coordination number, but only 3 bidentate ligand because each bidentate ligand forms 2 dative covalent bond there. And the charge is going to be 0. They haven't asked you that, but the charge definitely cancel out because this is a -1 charge. When you have 3 bidentate, you have a -3 overall. Cancel out the chromium +3 because in this reaction, you also kick out 6H2O, by the way. This is simply what you call a ligand substitution. These are ligand substitution because you are replacing the monodentate water with this bidentate ligand Z, and this is not a redox. If it is not redox, that means the chromium plus 3 is still chromium plus 3 in the end. Part 4. So what we have, oops, sorry, not part 4, but part D. So this is question 2, part D. This is oxidation number. So we have this compound called ammonium dichromate. There are two ways of doing this. If I were you, I would be thinking about ammonium. Ammonium is NH4 plus. So NH4 plus, there are two of them. So therefore, we are looking at Cr2O7 2 minus, which of course we know from AS as part of a common oxidizing agent. This is called dichromate 6. If you know it straight away, then you should be able to get the oxidation number as plus 6. But if you don't, then you know the oxidation number of the ion is minus 2, following the revelation that you have two of these plus 1. So the balance is minus 2 to give you an overall compound with no charge. Minus 2 equal to the oxidation state of chromium times 2, because I have 2 chromium, plus 7 times minus 2, 2 chromium equal to plus 14 minus 2, chromium equal to plus 12 over 2, chromium is plus 6 there. As you know, dichromate 6, chromium plus 6. Without the plus, it's not going to make any sense at all. Cr2O3, overall compound has no charge, so oxidation number is 0. I've got 2 chromium, I've got 3 oxygen, each of which is minus 2. So 2 chromium is plus 6, chromium is plus 6 over 2, chromium is plus 3 in Cr2O3. Next up, what do they want us to do? They want us to write a balance equation for the decomposition of that. What I'll do is I'll move this up a little bit because I'm running out of space here. We can think about a redox equation in the context of change in oxidation number must be balanced out. Okay, that's probably the angle at which they want us to do this in. They will decompose to give you Cr2O3 plus H2O plus an inert colorless gas. Inert, first of all, is an inert. Inert means unreactive. So inert, colorless gas. The fact that it's inert would imply there's N2. The fact that it's colorless would imply that it's not NO2. And it's not oxygen as well, because oxygen is not completely inert. NH3 is not inert. So we can be safe in confidence that it has got to be N2, because there's no nitrogen in here at all. There's only nitrogen left that I need to balance the equation. Anyway, so what do I have? I have chromium plus 3. I have chromium plus 6. And to think about the nitrogen as well, if I have the nitrogen, I think it's best if I actually move this onto a new page, because again, I don't want to be running out of space when I do this kind of question. So this is question 3, or was it question 2? It was question 2, so question 2 part D. And it's the last part to that. I'm trying to show the changes in oxidation number. So we remember that the nitrogen they come from the NH4 plus. So the overall oxidation number NH4 plus is plus 1. The nitrogen is unknown. I have 4 times plus 1 hydrogen. So the nitrogen is plus 1 minus 4. Nitrogen is minus 3 there. What happened there is nitrogen 0. So what can I say? Nitrogen minus 3 to nitrogen 0 is an increase of 3. Whereas if I look at the blue one, chromium plus 6 to chromium plus 3 is a decrease of minus 3. Changes in oxidation number must be balanced. However, be careful, chromium is for 1 chromium. So I have 2 chromium there, which means I have 2 times plus 6, and I have 2 times plus 3. So altogether I have plus, what do I have actually? I have plus 12, I have plus 6 there. So altogether I have minus 6, to be honest. And here, nitrogen is for 1 nitrogen. I actually have 2 nitrogen. So actually I will have 2 times nitrogen minus 3. But I only have 1 times of that nitrogen 0. So again, that should be plus 6. But happily, my minus 6 will cancel out plus 6 as well. So, you know, very, very easily you get one of these. That should give you one of these, because 2 nitrogen and 2 nitrogen, 2 chromium and 2 chromium, 7 oxygen, 3 oxygen, so 4 oxygen. I need 4 more oxygen there, so it's got to be 4 there. And the hydrogen is 8. The hydrogen is 8. Everything is balanced, so you get a balanced equation just like that. If I just write it out neatly, So this equation, probably you don't need to use changes in oxidation number to balance this equation, because it should be quite easy to balance after all. But it's probably a lot easier if you just think about the oxidation number, no changes at all. Well, I mean, there's a change, but you know, they're balanced out. So in that regards, they become easy because one of that, and one of that. So you're just balancing out the atoms, which is just from the water. So that's it for that 15-mark question, number 2. Question 3 is also a transition element question. So define the term transition element. I think I talked about it earlier when we cover question 2. So transition element forms ions or compounds with partially filled d orbitals. Okay, so you must have electrons in the d orbitals, but it must be partially filled. It cannot be zero. It cannot be fully filled. Now state how the melting point and density compare with your calcium. There are two things. The melting point of transition metal is a lot higher. So the melting point of iron is a lot higher than calcium. So this is just stating. They're not asking you to explain. The transition metals melt and boil at a higher temperature. Transition metal also has a higher density. So density of iron is higher than calcium. So I am just stating, I am not explaining. B part 1. So this question is actually about not really about transition metal, it's actually about electrochemistry. They want us to define standard cell potential. So there are two bits to this definition. First of all, you need to know what the standard conditions are. So standard, they refer to standard conditions, which is 298 Kelvin, 1 atm pressure, and of course, in the context of electrochemistry, we're also talking about 1.00 mole per dm cube. And then we're talking about cell potential. We're not talking about electrode potential, so be very careful there. I've always remember my definition of standard cell potential as a measure of the tendency of electrons to flow through external circuit. If you don't like this definition, you should go for the other one, which is to do with the maximum. So this is in fact probably much better. So the maximum potential difference, the moment you see this term called potential difference, is to do with two electrode system. So it's between the electrodes under standard conditions. So this second one is probably a lot more complete compared to this first one. So I can write down my standard conditions straight away. 1 atm pressure as well as 1.00 mole per dm cube concentration. Okay. I guess what I can do then is probably just put this into, a square bracket, not a square bracket, a square box there, so that you can probably think about it with regards to what is being asked there. The next part is, not surprisingly, they do want to give you some free marks. So they give you the opportunity to actually, get some free marks here and there. You're expected to draw a fully labeled diagram for 3 marks. So if I just label my apparatus, nope, I don't want a curve. I want a bigger container, another container. I will have a high resistance voltmeter, and I'll have a salt bridge connecting these two together. I have a metal ion and a metal, so I will need a metal electrode there. I have a metal ion and a metal ion, so I need another metal electrode there. But here I need an inert electrode, which is platinum electrode. But on the other side, I will need a copper electrode because I have a metal and a metal case study. A metal and a metal ion, a metal and metal ion means I need 1.00 mole per dm cube Cu2 plus aqueous, which could be from copper to sulfate if you want to. And then this is a metal ion and metal ion, so I have 1.00 mole per dm cube ion 2 plus aqueous, and also 1.00 mole per dm cube ion 3 plus aqueous. and this is equimolar after all. Okay, so this is a metal ion and metal ion case study, so I need a platinum electrode. This is a metal ion and a metal case study, so I need the metal as the electrode itself. I haven't completed the circuit until I label the salt bridge there, and I also need to label this as high resistance voltmeter. So the idea of high resistance is so that they will allow you to measure the potential, the maximum potential difference, which was actually the definition for E cell. Include all necessary reactants. I did that. I should probably just mention this is at 1 atm pressure, 298 Kelvin or 25 degrees Celsius on the side there. Question 3, part C. So this looks like, this is actually part of catalysis. This is homogeneous catalysis. It comes under the last bit of the A2 rate of reaction topic. So they say use equations. If you read the questions, they say equations, there's plural, because this is catalysis. So you need to show the catalytic role of Fe3+. So if you think about it, the overall reaction is actually S2O8 minus plus I minus going to I2 and SO4 minus. This is not thiosulfate, this is peroxyl disulfate. It's a case study in A2 rate of reaction as part of the essay on homogeneous catalysis. So there's 2 of that, and there's 2 of the iodide as well. So overall, you can hopefully see that there's 2 minus and 2 minus. So you get 4 minus there, 2 iodines, 2 times sulfur, 2 sulfur, 2 times 4 oxygen, 8 oxygen. This is the overall reaction. I hope you can appreciate the idea is that this is a 2 minus and this is a minus. Negative charges repel. So negative ions repel each other. So that means if you want them to react, they have to collide with each other. That's going to give you high activation energy, slow reaction. So what is going to be your catalysis? Your catalysis involves reacting with iron. When you think about this, the iodine there is iodine -1, the iodine there is iodine 0. So that is an increase in oxidation number. So this is oxidation. My catalyst here, they say add a few drops of iron 3+. So iron 3+ doesn't want to go to higher oxidation state, so the iron 3+ will go to iron 2+. If the iron 3+ go to iron 2+, this is a decrease in oxidation number. This is reduction. If you want to do reduction of this, you need to find an oxidation partner. This is the one that get oxidized. This is the one that get reduced. So I start with the one that get oxidized first. So Fe3+ plus 2I minus going to I2. And of course that I need 2 Fe3+ and 2 Fe2+. Because, well, to balance out the changes in oxidation number, of course, and also to balance out the atoms. So this is 2 times plus 3 is plus 6, minus 2 is plus 4, 2 times plus 2 is plus 4. Positive ion and negative ions, at least no more repulsion, much lower EA, alternative reaction pathway, much faster reaction. This is one equation. This is showing that Fe2+ is converted to Fe2+, but you haven't shown that Fe3+ is a catalyst yet. So what happened is the Fe2+ will react further with S2O8 minus. If we look at our original equation there, that will give you the Fe3+ again, and they will give you the 2SO4 minus. Again, you need to balance the changes in oxidation number as per AS redox reaction. In the topic, they say use changes in oxidation number to balance chemical equation. So now this is oxidation, which means this is the reduction, which is the accompanying partner. Plus 2 times 4 is plus 4, minus 2 is plus, what am I doing? Plus 4, minus 2 is plus 2, plus 6, and then 2 times minus 2 is minus 4. So overall you get plus 2 on the right as well. So now you can hopefully see that Fe3+ is regenerated. And in doing so, now you have a plus charge with a negative charge. Again, this one will have much lower activation energy than the 2 negatively charged ions coming together. 2 equations, so 1 equation and 2 equations. They are not looking for this equation. This is just overall. It doesn't show the catalyst in there at all, because a catalyst is never used up in the reaction. They just simply get involved in the reaction. This is your intermediate, and then your intermediate further reacts to regenerate your catalyst. C part 2. So this is question 2, question 3 actually. So we have Fe3 plus can oxidize I minus, and then that blah 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 cannot oxidize I minus. I think we need to appreciate the idea of I2 plus 2 electrons going to 2I minus. We need to look at the E naught from the data booklet, which I am just opening right now. So I2 going to I minus is plus 0.54 volt. Everything in the data booklet shows reduction potential. Next up, I need to look at Fe3 plus aqueous. So they are in alphabetical order. Fe3 plus going to Fe3 plus plus 3 electrons. Going to Fe is minus 0.44 volt. Should probably ignore that E naught there. And then I also have another Fe3 plus going to 2 electrons, which is the one above it. Oh no, sorry. The one below it is actually Fe3 plus plus electron going to Fe2 plus, that is plus 0.77 volt. Which other one am I looking at? Something that has got Fe3 plus in it. Okay, so the other one is FeCN6, 3 minus, plus electrons going to FeCN6, 4 minus, and this is plus 0.36 volt. So we look at what happened there. So they say that I minus is your reactant. They say I minus is your reactant. So this is your reactant. So we are going this way, which means this is our EOX because we are trying to lose electrons. This is the EOX, which means we need to find ERAT. If this is your EOX, and we know, so we gotta use E naught values to explain these observations. In terms of all this, your ERAT has to be more positive than your EOX. This is iron 3 plus. If you want the iron 3 plus to oxidize this, the iron 3 plus itself has to be reduced. The iron 3 plus itself has to gain electron. So this is going to be more positive. It should be more positive than the EOX, but this is less positive than EOX. So it's not going to go to iron. Okay, so this is not what we are looking for. I can cross this out. They say use E naught values to explain the thing. So I should really, list down all these things as part of my explanations, because although these are from data booklet, you really need to list it down in your answer in order to explain it. Okay, so how can I explain it then? Between this and this. So this being the ERAT, because I'm doing the reduction as I'm going this way. So that is reduction. So those are going to be my ERAT and ERAT. So for oxidizing I minus with Fe3 plus, the E cell is equal to ERAT minus EOX. So the ERAT is going to be more positive than that. So plus 0.77 minus plus 0.54. And you can see that there is going to be a positive number. I'm just going to press into my calculator. I get plus 0.23. Your calculator actually doesn't show you the plus, but you must have sign, value, and units for this kind of question. Therefore, feasible and spontaneous. As you know, when the E cell is greater than 0, the reaction will be feasible and spontaneous. On the other hand, with FeCN6, 3 minus, the E cell, again, our ERAT there is going to be that. If we want to use these to oxidize the I minus, that means this one get reduced and this one gain electrons. So if that is your ERAT, plus 0.36 minus your EOX, which is still the same, oxidizing the I minus going to I2, plus 0.54. So this is a hypothetical situation, and we are just using our E naught value to work out whether it's possible or not. Here, this is minus 0.18 volt. So this is lesser than 0. So this is lesser than 0. Therefore, not feasible and not spontaneous. Not going to happen under room temperature and condition. So that's the whole idea of using E naught in order to do this kind of question. Using E naught, explaining whether it's feasible or not. Alright, so for that 2 marks, should be able to write out or state these equations with the correct E naught values and do a bit of simple calculations for E cell to work out whether feasible or not feasible. Question 3, part D. This is related to the previous question. So here, instead of iodide, you have the tartrate. So tartrate looks pretty much like the iodide in the context that, still -1 charge. So it is still something which is negatively charged. If I just write that down, so well, actually it's -2 charge. It's a dicarboxylate, like that. If you draw the skeletal formula a bit better, it should be written like this. Okay, so this is just a more complete skeletal. This is what is given. So why is it still slow? Slow without catalyst. Slow without iron 3 plus catalyst. It was the same reason as I mentioned just now. High activation energy, high EA, because above the reacting particles, in this case they are ions, above negatively charged, therefore repel each other. So very slow reaction there. And in part 2, so we gotta use the overall equation. I guess the fact that they say use the overall equation to deduce, so we can think about the overall equation being the redox equation, where we have the oxidation plus the reduction half equation. So I can immediately see the S2O8 2 minus going to SO4 2 minus. This is a bit tricky because as far as, oh yeah, okay, I think I get it now. So there's usually 2 times that, because 2 times sulfur give me 2 sulfur, 4 times 2 give me 8 of that. And you can imagine balancing the charges. There is 2 minus times 1 is -2, 2 times -2 is -4. So this is going to be a reduction. You need 2 electrons on the left hand side. So -2 give me -4. So -2 times 2 is -4. So this is one of your balance equation. This is a balance half equation for reduction, because you are gaining electrons. So gain of electrons is reduction. So reduction is gain of electron there. What you could see very obviously is that this is 6 in the equation. So meaning to say they multiply that by 3 such that you get that. So obviously you don't write all of this down in the actual exam, but this is the way you're thinking in your head, that you have the whole thing multiplied by 3. You're looking at something with 6 electrons. So there's something that you have to include in your half equation for that question part 2, because changes in oxidation number is in terms of the electrons. If you have 6 electrons as a result of this equation, you must have lost 6 electrons from the ethane, not the ethane, but the tartrate ion there. So if I write C4H6O6 2 minus plus something, that will definitely give me 6 electrons, because I'll have 6 electrons on the right. Looking at the overall equation, if you cut out the 3S2O8 2 minus, if you cut out the SO4 2 minus, what we are left with is just whatever on the left. So the 1 of the tartrate plus 2 of the water, I will get, what do I get actually? I get 2 CO2, I get 2 HCO2 minus, I get the 6H plus as well as the 6 electrons. 6H plus and 6 electrons. The 6 electrons is what I add in, because these are not included in the original overall equation. I'm just simply taking out the 3S2O8 2 minus and the 6SO4 2 minus from the equation, such that this is whatever is left on the left, this is whatever is left on the right. I know 6 electron there because if I know these half equations, then I know I need to have 6 electrons if I multiply the whole thing by 3 there. Okay, or of course you could balance everything, and then in terms of charges, -2 times 1 is -2, no charge, overall is -2 on the left, 2 times -1 is -2, 6 times +1 is +6, so this gives you +4, +4 to go to -2, so +4 to go to -2, you need to gain 6, you need to have 6 electrons on this side, meaning to say you're doing oxidation, which is loss of electrons. That's how you can balance this equation very, very quickly as well. To the next part of this question, E part 1. So this is a lot more organic reactions. We got to complete this table. They want the organic product. they have simply said structure. They don't mention display, structural or skeletal. They just say structure. So I personally would draw skeletal because that is my favorite. I don't know what your favorite is, but this favorite of mine is fast, it's elegant, it's easy once you know what is going on, and it's something that you have to get used to if you want to do well in an exam. Master your skeletal formula. Okay, so the first reaction there is excess of lithium aluminium hydride. This is a reducing agent, so it's a source of H minus. It's a reducing agent, so it will reduce your carboxylic acid all the way to your primary alcohol. So I will get alcohol all over from the original carboxylic acid, but I need to be careful. I have done something wrong here. I've gotten 2 carbon, whereas I should have 4 carbon to begin with. You see, when you draw skeletal formula, you need to be very careful about what you're drawing. Otherwise, you might lose the carbon. So let me just draw that again. Carbon, oxygen, and then OH there. So this one is going to be 1, 2, 3, and 4. There are 4 carbon, just like there are 4 carbon in tartaric acid. If I draw out tartaric acid, that was the tartaric acid that is given in the question. So we're talking about this particular carboxylic acid and this particular carboxylic acid. They get reduced all the way to the primary alcohol there. This type of reaction is called reduction. On to the next one, you have an excess of CH3COCl. This is what you call acyl chloride. That is the class of there's a functional group in reality. The name itself is called ethanol chloride because there are 2 carbon acyl chloride, just like that, 1 carbon, 2 carbon. Acyl chloride is a reactive version of a carboxylic acid, such that you don't need a corn sulfuric acid as a catalyst in order to form ester. So this behaves like a carboxylic acid, meaning to say your alcohol will be untouched. So your alcohol is untouched. Oh, actually, no, your alcohol, it will be the one that reacts. What am I talking about? So your carboxylic acid will be untouched, like that, but your alcohol will react, and they will have 2 carbon ester like that. They will have 2 carbon ester like that. So you can hopefully see that, you know, this thing there come from the ethanol chloride. This thing there come from the ethanol chloride. That's the one that behave like carboxylic acid. They will form ester with your alcohol. They'll form ester with your alcohol. You use excess of it, so you can never stop at single ester being formed. This reaction has a name called esterification, but they are specifically looking for type. A lot of students are confused between type versus name. In your AS introductory organic chemistry, there's a list of the type of reaction. None of them contain esterification. That's because esterification is the specific name for the reaction, whereas the type is going to be condensation. When you form an ester, it's called a condensation reaction. You have learned this in IGCSE or O-level chemistry as part of condensation polymerization, and you have learned it in AS, and you learn it again in A2 as part of condensation polymerization when you form polyester or polyamide. On to part 2. So what we have then is, this is the last bit of this question. This is E part 2. So tartaric acid reacts with amine. So if I just redraw tartaric acid, because a lot of this type of question is a lot easier if you have the structure in front of you. So this is tartaric acid, and they will react with phenyl, 1-phenyl ethyl amine. So I have a phenyl, which is C6H5, and then CH, and then NH2, and then CH3. This is actually oh wait, I was going to say amino acid, but this is not amino acid. And they said that they will form an ionic salt. So show the structure of the salt. This is an amine. So an amine is a base because it's got a lone pair on the nitrogen to accept proton. So it's a proton acceptor. Which one is going to donate you a proton? Well, you have 2 groups that can donate protons. This is your carboxylic acid. Your carboxylic acid is pH lesser than 7 because that is an acidic group. Same thing there. There's another carboxylic acid group. So when you have they say an ionic salt. Okay, so the key thing here really is the question say an ionic salt, and then they say draw the structure of the salt. So in accordance to what the question is saying, there's only one salt that you're forming. I will be tempted to say that, both of them will get deprotonated rather than an option for one of them getting deprotonated. So there's all minus like that, and there's all minus like that. And what I'll have is I'll have the phenyl ring, and then I have the methyl group, or I can have NH3 plus like that, and then the methyl group, and then I can draw another one. So my phenyl or my benzene ring is not drawn very well. Gotta improve on my drawing of that. I had drawing that 6-member ring actually. Okay, that's as best as I could do. Hang on, it's bonded to carbon, and that carbon has got NH2, which is now protonated. Now it's NH3 plus. I have an all minus and all minus, so I have one of these there and one of these there. So make sure that you are not forming covalent bond between this and the nitrogen, because the nitrogen is a second period element. They cannot form more than 4 covalent bond there. So this is going to be the structure of the salt that you are forming there. Don't know if I can draw it in a box. Would it be better? I don't think so. Yep, it looks better there. So the structure of the salt form is a dianion, so you get dication as a result of that. Lone pair accepting H plus, so you need 2 of them because both of them get deprotonated. They want the salt. That's the end of that 17 mark question number 3. Question number 4 seems to be chemistry of copper, which is to do with transition metals. So this is a fixed case study. You can watch my A-level concept tutorials. Is it in there? No, probably in the experimental tutorial playlist, where I've actually shown and demonstrated these reactions, a series of experiments, series of ligand substitutions, where you could actually see the color changes rather than just, reading books and knowing all these color changes just by reading. It's better to have seen it. Ideally speaking, in the real world, you should have done these experiments, and you learn by doing, and that's the best way to learn chemistry. Alternatively, in light of COVID, if you can't go to the lab, you can watch my experimental tutorial videos. Perhaps that can help you to some extent. So what we have here is we have copper 2 plus aqueous ion is actually copper hexa aqua complex. So this is equal to copper 2 plus aqueous. What we have excess sodium hydroxide. So our color and state, they want 2 things. They want color and state of the copper species. So the color is going to be a pale blue, and then it's a precipitate. So precipitate means it's a solid. Okay, so I have described the color and I described the state as well. Ionic equation. Ionic equation must have stat symbols, whether they ask you to or not. So what actually happened is the copper H2O 6, 2 plus aqueous, plus the 2OH minus aqueous. What happened is you get copper hydroxide as a precipitate, and there will be a solid, and it will kick out the water, which is going to be liquid, and then don't dissociate further. So this is a precipitation reaction, and this is what you have done for precipitation ionic equation. It's just adding in the water as a result of kicking out the 6 monodentate ligand there. What type of reaction is this? This is a precipitation reaction, as you are forming a precipitate from 2 solution. This is a pale blue solution. This is a colorless solution. You get a pale blue precipitate, insoluble in excess NaOH. Part 2 is about with excess ammonia, excess aqueous ammonia. So what is going to be the color and the state? Well, you are going to, first of all, actually you're going to get this thing, which is a pale blue precipitate. However, ammonia in excess can act as a ligand. So this thing can act as a ligand and replace the OH minus, such that you get copper with 4 ammonia. So it's an incomplete replacement, unlike with cobalt. So this is just 4 ammonia, but 2 water, so it's still octahedral complex. Each of these ligand has no charge, so it's still copper 2 plus like that. They are asking for the color, so they are not asking for this thing. That is actually for the next bit. So the color of this is actually a dark blue. and it's a solution. Solution meaning aqueous state. Okay, they want the color, they want the state. Now I need the ionic equation for this thing. So what happened is I started out from copper H2O6 and then 2 plus. I have 4 NH3 and I will get this particular dark blue complex. And what happened is I only kick out 4 water. I only kick out 4 water and replace them with ammonia. So I still have 2 H2O there. Okay, so let me get rid of that. I don't know what happened there. Okay, so I kick out 4 H2O. Be very careful to write your equation balance. 6 water give you 2 water remaining. So you kick out 4 water, only 4 ammonia replace 4 of the water. It's an incomplete substitution to give you that dark blue complex. It's a feature quite special and quite unique to the copper chemistry. And this type of reaction is no longer a precipitation because all of these are aqueous. Pale blue solution, colorless solution, dark blue solution, and liquid water colorless solution. Well, colorless liquid, not a solution, because all of these are dissolved in water. You can watch my experimental tutorial video playlist, especially on the one on copper 2 chemistry, where I demonstrated these color changes. So these are ligand substitution reaction, where we have substituted one ligand, which is the H2O, with NH3 there. To the next part of the question. This seems like a very, very short question actually. So part B, we have copper 1 oxide. Be very careful. Copper 1 oxide would mean that you have Cu plus and O2 minus. So the valency there is 1 and 2. So when you cross multiply it, you're going to get the LCM. This means copper plus, and you're going to get O2 minus, Cu2O. This is going to be copper 1 oxide. So be very careful with your formula. I'll probably copy paste this onto a new page because I don't want to run out of space. So what do we have here? We have copper 1 oxide, Cu2O, reacting with H2SO4, which is sulfuric acid. You get a blue solution. By the way, this is actually a brick red PPT because this is the PPT that you get when Phalanx reagent reacts with aldehyde. Think about Phalanx. Phalanx reagent is pale blue solution. And then when you have aldehyde, if aldehyde is present, you're going to get brick red PPT. And that brick red PPT is copper oxide. Copper 1 oxide specifically. So there's brick red solid plus that. You're going to get a blue solution. Very clearly, the blue solution will indicate the presence of copper H2O6, meaning copper 2 plus aqueous, and you get a red-brown solid. Red-brown solid. Unfortunately, I said this is a brick red PPT, but you also get a red-brown solid, which is actually not going to be. What am I talking about? Let me think. What is this? I think the red-brown solid is not going to be copper 2 oxide because copper 2 oxide is actually kind of black in color. So CuO is black. CuO is a black solid. So meaning to say this brown color precipitate, this red-brown solid, it's not likely to be the copper oxide. I think it's going to be copper metal. But copper metal is usually described as a pink or salmon kind of color solid. Let me just try and balance this equation from scratch first. Copper 2 oxide plus H2SO4. So I get CuSO4. And I can get copper. And I can get water. Is that correct? Probably. So the copper SO4 can dissolve in water to give me the blue solution. I have 2 copper, 1 goes there, 1 goes there, sulfate there, H2 goes there, O goes there. This is the complete balance equation, so this seems legit. Copper to sulfate and water, so these two together will give you the blue solution. So my hunch is kind of correct that it has got to be copper, which is the red-brown solid there. So X is the blue solution, so there is copper to sulfate, aqueous, and then Y is going to be copper solid. This is actually going from copper plus 1, copper 1 oxide, to copper plus 2, copper 2 sulfate, and copper 0. This is what we call, it's not really disproportionation, but it's kind of like reverse disproportionation. No, actually it is disproportionation, sorry. Disproportionation, because it is one species is both oxidized and reduced in the same reaction. Plus 1 to 0, that is reduction. And then plus 1 to plus 2, that is oxidation there. Plus 1 to plus 2 is an increase in oxidation number, that's oxidation. So this reaction is called disproportionation. That's the end of the end mark question there. Question 5. So we have reached rate of reaction now. So we're looking at how to monitor this reaction. This question is a bit tricky because they say something about inert solvent. So we are not using water, they are just using inert solvent. They represent it as S or LV in a bracket. So inert means unreactive, it doesn't react with your reactant or whatsoever. What can we see here? We have N2O5 in the solvent going to 2NO2 in the solvent plus half O2 as a gas. How can you monitor this reaction? That's the question. How can you monitor this reaction from the given information? The thing is, usually we will be looking at NO2, which is a gas. So usually it's a gas and it's a brown gas. But here it is dissolved in the solution. They say based on this information, so I would say to monitor the rate, I'll probably collect the volume of gas here. This seems to be more legit, but it's just me. And looking at the questions, they do say measurements. If you think about the plural, why do they give us plural? Because rate is the change in amount over change in time. So we got to monitor not only the change in amount, but the change in time as well. So in terms of the two things we need the volume. We can monitor the volume of O2 gas produced over a fixed time at regular intervals. So intervals meaning time intervals, and they are not asking us for the apparatus, but this is what you would use. You will use a stopwatch, and then to monitor the volume of gas produced, you will collect the gas. You can use a gas syringe in order to collect the gas, a stopwatch to monitor the time. So the change in the volume of gas produced over the change in time is going to give us the rate of reaction. They did say measurements, plural, so I'm giving two things that we need to record. It's a suggestive question. I'm not entirely sure if this NO2 will be colored in solution or not. Not a solution, sorry, in the solvent, because they don't say it's in water. The fact that we know it's a brown gas does not mean it's necessarily the same color in this particular solvent. That's why I don't want to go onto that route. Rather, I focus on what I can do better, which is to collect the gas. Part B, so question B, they are asking us, they give us a graph of how the N2O5 changes with time. So B part 1 is explain half-life. So these are basic definition. What I mean is you gotta be ready for this kind of definition. So it's the time taken for the initial concentration of a reactant to fall to half its initial concentrations, to half. Okay, so it's the time taken for that initial concentration to go to half its value, or to just half, HALVE there. Now determine the half-life of this reaction. Show you're working on the graph. What I'm going to do is I'm going to have to copy the graph and then paste it here. So otherwise, it's impossible for me to actually do it without doing the graph. I hope that will be alright. If that's not alright, then I'll just re-edit this video and take out the whole graph again if I'm being told that they'll violate whatever copyright thing again. Okay, so just give me a minute. I'll stop this video, and when I come back, then the graph will be here. Okay, I'm back and this graph has magically appeared because I just copied it from the question paper. Okay, hopefully it'll be alright. Now they say show your working on your graph. If they want you to show your working on your graph, you gotta have a line. And I started with 0.25 mole per dm cube, which means when I halve it, so 0.25 divided by 2, I get 0.125. 0.125 is somewhere there, so that is 0.125 mole per dm cube. So if I do it like that, then I will get somewhere in between there. So to read that carefully, there's 100, there's 200, so there's 120, 140, so there's 150 second there. You can't really actually do half-life just by the first one, but let's do a second one just to confirm what we are thinking. 0.125 divided by 2, I get 0.0625. This is 0.05 there. 0.06 is the next one, so I want 0.0625, give or take somewhere around there. Some people will say, oh, it's not very exact. Oh well, tough luck, it's just a graph. Then you have 250, 267, there's 280, so between 280 and 300 is going to be 290 seconds there. So as you can see, the first half-life there is 150 second. The second half-life between 150 second to 290 second, give or take, there is around 140 second. But again, I haven't been super exact, so I'm just trying to estimate a little bit here. I would say the half-life is pretty much constant there, pretty much confirming that it is first order with respect to N2O5. What do they want us to do? In part 2, they just want us to determine the half-life. I can just do the first one, which is just the green color one, so that is going to be 150 second. Always have a unit of the time based on the graph itself. On to the next one. So part 3, what is the effect on the half-life if the initial concentration is half? Well, if I look at that question is basically a repeat of what I have just said. I have said that, the second half-life, oops, I really don't want to do that. Perhaps I just go to the next page. Part B3 is asking you if the initial concentration is half. So that means we start from here. What is going to be your half-life? Your half-life is going to be, when you halve this again, it's going to be from here to here. It's about the same. So I can see that, this is suggest the effect. So did they tell us it's first order? They did tell us it is first order. In the question, if you look carefully, just above part 1, the reaction is first order with respect to N2O5. So that means constant half-life. There is a given for first order reaction. Now they ask you to suggest what happened when you halve the concentration of that. There will be no change at all. So half-life remains the same, or it remains constant, because we know already in the question they already told us that it is first order with respect to N2O5 back on page 10 just above part 1 question. Moving on, so C part 1, use your graph to determine the rate at 200 second. Very specific, at 200 second, we need to draw a tangent at 200 second. A tangent, because this is a curve, you cannot get gradient of a curve unless you know the equation, then you can do calculus. But given a graph like this without equations, the best thing I can do is draw a tangent. So let me just change the color. Not too sure how well this graph will be. No, that is not good enough. I want my tangent to be centered at 200 there. So what I can do is, let's play around with this. That is actually not good enough as well. So perhaps I can do this. That is probably better. So what you would do on your ruler is you extend this a little bit like that. I can do it very easily on my screen, but it's probably a lot easier on your paper as well. But you move around until you have a tangent at t equal to 200 seconds based on the question. If I were you, I wouldn't be focused on reading other coordinates. This is 0, 0. This is a perfect triangle, so I might as well just read the y-axis and the x-axis. The y-axis there, it cut at 0.19, so it's 0.19 minus 0.00, meaning the change in y, 0.19 minus 0.00, divided by the change in x, so delta y over delta x, as you know, is going to be gradient of the tangent. So that cut halfway in between 400 and 420, so there's around 410 seconds. On the x-axis, 410 minus 0. You have second on the x-axis, you have mole per dm cube, and there's no other thing given in the information there, so you know that is going to be my gradient, which I'm going to copy paste and put it here now. So just do that on your calculator. You get 0.19 over 410, 0.19 divided by 410. They don't tell us how many significant figure, but let me look at the question. If you look at the data given, these are 1 and 2 decimal place, or you can think about 1 and 2 significant figure. So I think what is appropriate number of significant figure is going to be 2 significant figure. So 4.634 times 10 to the minus 4. That is purposely done in order to, you know, before I run up, so that I just want 2 significant figure. I look at the next one, so 4.6 times 10 to the minus 4. Do not forget unit. Out of good habit, you should always have unit in your answer. 2 significant figure was chosen based on the data given in the table. The concentration N2O5 was given to 2 significant figure. To the next part of the question, C part 2. Use your answer to C part 1 as well as this red equation. So red equal to K N2O5 to the power 1 first order. I want the red constant, so K equal to the rate over the N2O5. If I have at 200 seconds, this is my rate at 200 seconds. What is my concentration of N2O5 at 200 seconds? The concentration of N2O5 at 200 seconds, reading from your graph, at 200 seconds, so this is the point there, at 200 seconds, the concentration N2O5 is 0.10 mole per dm cube. So 0.10 mole per dm cube. I have my expression there, so I will just, you know, move it down there and go up there. So now I am ready to put in everything. So 4.6 times 10 to the minus 4 mole per dm cube per second. They say use the answer to the previous bit, which I'm doing, and then I have 0.10 mole per dm cube. The mole per dm cube and mole per dm cube will cancel, therefore giving you a unit of second minus 1. That will be 4.6 times 10 to the minus 3 second minus 1. They do want you to give the units for the red constant as well. Last but not least, don't have much space down there. Perhaps I can finish this without writing a lot. So we're looking at another equation. So rate equal to K, NO2, NO3. I think I better move on to the new page because I think I can talk a little bit about this. And this basically means first order. And this is first order. And it's with respect to that particular reactant, with respect to that particular reactant. And we have these 2 NO2 plus O3 going to N2O5 plus O2. We know it's 2 steps. We are asked to write down 2 equations, 2-step mechanism. So what's going to happen is, in the slow step will be whatever that appear in the red equation is going to be in the slow step. So there is 1 time NO2 in the slow step and 1 time O3 in the slow step, in the red determining step. That's the meaning of red equation. That's the meaning of red determining step. One of them is involved in the slow step. Overall equation, there are 2 of them. So perhaps what I can do is I can set NO2 plus O3. That will give me, and if I have O2 as well, then the O3 become O2. That means this become NO3 maybe, something like that. And what happened then is the NO3 will react with another NO2, and I'll get NO3 will react with another N2. So another NO2 will react with another this NO3, which come from these and these. They will give you N2O5. When you look at the equations, 2 of these plus 1 of these This and this will cancel out because they are intermediate in this reaction, and they give you one of these and one of that. So this is consistent with the overall equation, and of course this is now a two-step mechanism, and I can tell you the first step is going to be what you call rate determining step. It's the slow step because one of these and one of these, as stated in the rate equation, one of these and one of these affect the overall rate of reaction because they appear in the slower step of the reaction. This is a possible two-step mechanism. Okay, and this can't be your first step because this has to come from somewhere. This is your intermediate, which you produce from your first step, and then you get your final product after you react to the intermediate with another one of these NO2. Okay, so that's the end of this 9-mark question on rate of reaction. Question 6 start off by asking you this fixed essay. So there are quite a lot of these kind of fixed essay question. This is a 4-mark fixed essay, so you gotta be prepared for this kind of thing and scenario. They want you from the most acidic to the least acidic. So we gotta try and think about these things and compare them one by one. Butanoic acid is a 4-carbon carboxylic acid, and we have ethanol. Ethanol is 2-carbon alcohol, and we have ethanoic acid, a 2-carbon carboxylic acid. I don't know why my carboxylic acid is not drawn very well, but anyway. And I have water. Water is just H2O there. Okay, the first thing I can say in my essay is I don't want to write down the answer first. Okay, so these are the given one. I really don't want, I'm not saying that, these are from most acidic to least acidic, so I leave a question mark there. Okay, so the first thing in my essay is I would say the more stable the conjugate base, the more stable the conjugate base. Conjugate base is the species you get after the acid donates the proton. So the more stable the conjugate base, the more acidic is the substance. The more acidic is the substance. So which one can I compare first? Out of all these three, out of all these four, I think I can compare the carboxylic acid first. Carboxylic acid are most acidic as the carboxylate. The carboxylate, the negative charge on the carboxylate can be delocalized through the CO pi system. I'm just going to demonstrate it now. So example, when you have CO minus like this, and then you can donate that and give you this resonance structure, this alternative structure, so you can delocalize these electrons, not just on this oxygen, but also delocalize it over the carbonium, and you can get two equal structure there. I've just shown an example there. It's the same thing for this butanoate, but our question really is, among the carboxylic acid, which one is going to be more acidic? Now, when you have a butanoic acid versus ethanoic acid, so we are comparing this thing versus this. So this is a 1, 2, 3, 4. This is a 1 and 2. Which one is going to be more stable? This is a CH3 group that donates to that ethanoate, and this is a CH3 CH2 CH2 that donates to this. So you can think about the electron donating effect. So in terms of the electron donating effect by inductive effect, so these are straight from the topic on inductive effect and electron donating groups of the alkyls from the stability of carbocation. Here we have a negative charge. More electron donating means you will destabilize the negative charge. So therefore, more electron donating, CH3, CH2, CH2 compared to CH3 means destabilizes it means it destabilizes the conjugate base more. Destabilizes the former or the previous, the conjugate base destabilizes that thing there. 1 2 3 4 or minus more. Therefore this thing is a weaker acid than ethanoic acid. Okay, so we got our first trend there, and this effect there is called inductive electron donating effect. Yeah, inductive electron donating effect of the alkyl groups. Onto the carboxylic acid. Well, carboxylic acid is definitely more acidic than the water because it's a more acidic group compared to the other one. Onto alcohol and water. So if we look at alcohol versus water, so if I have alcohol, then this is the conjugate base versus HO minus. Now we can see that the alkyl electron donating group on the alkox side, or I can say etox side, meaning CH3, CH2 or minus. Okay, by inductive effect will destabilizes the conjugate base more than just the hydrogen does for OH minus, because the hydrogen just, it just form a covalent bond. They don't do that donation of electrons because oxygen is naturally electronegative to begin with. Therefore, we can say that H2O, we can say that the alcohol CH3 CH2OH is going to be less acidic than water. So now I am ready to state from the most acidic to the least acidic. So the most acidic is going to be, if you compare the carboxylic acid, this is weaker than this. So this is going to be the stronger acid. So you start from ethanoic acid. And then you follow that by butanoic acid, as I've explained why butanoic acid is a weaker acid than ethanoic acid. And then between water and also the ethanol, we compare the stability of the conjugate base. This is more destabilized, so this is going to be more stable compared to this. So this is going to be giving us water as being more acidic compared to the ethanol. So ethanol is the least acidic after all, because the conjugate base is the most destabilized. As a result of that, at least here you might think the electron donating group destabilizes the negative charge. It does to some extent, but you remember you can also delocalize over the carbon-oxygen carbonyl pi system. That's why carboxylic acid is always going to be more acidic than either of these two there. So that's the end of that 4 marks essay question. On to part B. So this is question 6, part B. These are a bunch of tests. So some of them you get observed results, some of them you don't get observed results. And you're supposed to complete the table with the reagents and conditions for a positive test. So we have test number 1, and we have reagents, and we also need to write down the conditions as well. So I don't want to copy down the whole entire table, but I might have to actually. So CO2H, and then I think I'll just draw the skeletal formula because it's a lot easier based on what I will do in a little bit anyway. So there's methanoic acid, and then that is going to be ethane-dioic acid, and the next one is propane-dioic acid, I think. CH3, CH2, no, sorry, butane-dioic acid. And then what is going to be observed change? I'm running out of space here. So what is going to be your change? Your observation. Observe change. So let me see if I can come up with this table very, very nicely. One of the perks of doing it on screen is I get to do all this without having to, worry about how neat I am. So yeah, let's try a different color. So test 1. So they said this is positive, this is negative, and negative. So what can react with methanoic acid? So methanoic acid is a case study in AS. whereas ethane dioic acid is a case study in A2 under carboxylic acid. So make sure you know these because they can ask you anything from AS in A2. So ethane dioic acid and this butane dioic acid cannot undergo this reaction, but this one can because you have one hydrogen there. So it looks like an aldehyde on this end. That's why methanol acid can be oxidized by Fellings and also by Tollens reagent. So what I can say is you can use things like oxidizing agent, but you cannot use KMnO4 because this can also react with KMnO4. So you want to avoid KMnO4, but what you can do is you can use Fellings or Tollens reagent because this group there looks like aldehyde. So you can use Fellings, for example. So Fellings reagent, and Fellings reagent you need to warm it as well together with this methanoic acid. And Fellings reagent is a solution of copper 2 plus to begin with. What you will get is you will get a brick red PPT, brick red precipitate, as a result of copper 1 oxide forming. After the methanoic acid there gets oxidized, the Fellings reagent get reduced from copper plus 2 to copper plus 1. Okay, on to the second test. What we have is, let's have a look at the tick and the crosses. So this reacts and this reacts, but this doesn't react. So these are just normal carboxylic acid. This ethane dioic acid can be further oxidized, but under extreme oxidation condition. So you need a very strong oxidizing agent, which is H plus and KMnO4, or you can write MnO4 minus. It's entirely up to you, but whatever you do, you must have the acid, otherwise there's no reaction, and you need to reflux this. Okay, so what happens is the methanol acid can be oxidized completely to give you CO2 and H2O. This will be oxidized completely to give you CO2 and H2O. So what you will get is you don't see the H2O and CO2. Instead, you see the purple KMnO4 aqueous. The solution gets decolorized, or you go from purple to colorless because the manganese plus 7 go to manganese 2 plus, which is manganese plus 2, and that is no longer the intensely purple color, from purple to kind of colorless or very pale pink. That's why you see this color changes. And assume these organic acids all have similar acid strength. Yep, that's all right, I guess. So that's it for the 3 marks. We now have the next part of the question where they want us to think about proton NMR. So this is B part 2. So number of peaks in the proton NMR, if I just copy down the structure because I can't be bothered to draw them again and again. So copy and paste them. Okay, but what I don't want is I don't need the line there. I don't need this. I can just move that a little bit apart so I have some space there. Okay, so let's have a look at the number of different proton environments. So they want the number of peaks in proton NMR. So the number of, well, basically proton NMR and then carbon NMR as well. Whew, okay, so they got this the other way around, which is okay. And that, which is okay as well. So if I have that particular table there, I could have proton NMR, how many peak, and then carbon 13 NMR, how many peaks. Alright, so carbon, let's do carbon first. Carbon means look for the number of different carbon. I just have 1 carbon there, so just 1 peak. I have 1 carbon and 2 carbon, but if you think about it, it's symmetrical. It's symmetrical, meaning both carbons are the exact same environment. So this carbon is exactly the same as that carbon. I still get 1 environment. Here, you're also looking at symmetry, which is symmetrical about the 2 carbons, but this is a carboxylic acid carbon, whereas you also get another carbon, which is a CH2 carbon. So these and these are the same, and then the red one, the red one and the red one are exactly the same. So altogether, you just get 2 carbon environment. How about proton environment? Proton environment, you got 1 proton, which is like aldehyde proton there, and then 1 for the carboxylic acid. So you got 2 proton environment, 1 there and 1 there. You only have 1 proton environment here because there's no proton on this carbon from 4 bond. So you can have a look at the structural formula and you can see it. I've just converted this to skeletal formula because for me skeletal formula is the easiest and the most elegant way to see through this thing. This proton is the same as that proton. By symmetry, there's only one proton environment there. Now to the proton for the last one. So this proton that I've underlined in green, they are exactly the same. And this proton there, which I'm going to show you there, so 2H there, is going to be the same as this 2H there. So altogether, you just have one proton environment and two proton environment, because this and this will appear the same place and this will appear in the same place. So that's it really, filling in the blanks in terms of how many different proton environment, how many carbon environment are there. On to the next part, which is to do with fast exchange. So they're saying that when you have this carboxylic acid, which is metanoic acid, and you have like that. Actually, why am I drawing display? They said that in D2O, then you can, what will it look differently if you compare the proton NMR here, which is two proton environments, compared to in D2O. In D2O, what can happen is I can write this equation, and in fact it's better if I write structural formula. So HCO2H, then what happens is the H on the end there will remain, but the CO2 can change the OH of the carboxylic acid with the deuterium of the D2O. So I get HOD. Deuterium is just heavy isotope of hydrogen. It's still the exact same thing. It's just no longer hydrogen. Here you have two proton environment, one there, which is no longer there, which is now which is now lost and part of the water now. Your molecule still have the hydrogen underlined in green there. So what happened is, this is what you call fast exchange. You can write an equation to show it. So as your reason number 1. So describe and explain. So this is your explanation. So the HCO2H undergoes fast exchange with D2O. The OH it's no longer present. Therefore, the peak due to OH disappears. Now only one peak in the proton NMR after this fast exchange. Previously you have two peaks as you have done in your table, one there and one for this hydrogen there. Now you have lost this peak as a result of fast exchange. It's no longer with a hydrogen, it's no longer with a proton, but now it's now with a deuterium, which is NMR inactive. Okay, that's the idea of fast exchange there. So on to the next part of the question. So this is still question 6. Question 6, part C. We have 1,4-dibromobutane. If I just convert that to skeletal formula, because you know how much I like skeletal formula. So there's 1,4-dibromobutane. And looking at that, this is a synthesis. So I get G, I get H. It seems like I need to work backward because they have given us the end product, which is J. And J is this HO, carboxylic acid, and then CH2, and then carboxylic acid. So this is 1, 2, 3, and 4. The next one is K. So this is H2N. So it's an amine. If you count the carbon there, 1, 2, 3, 4, 5, 6. So it's a 6 carbon. So 1, 2, 3, 4, 5, 6, and then NH2. Let's count again, because whatever you do, you always check. You count the carbon, CH2, there are 6 of them, CH2, 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 blah, 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 NH2 at the end. This is a diamine, so this thing are what you call amine. So this is a diamine. This is a 1,6-hexadiamine. 1,6-hexadiamine. I think I got this the other way around. 1,6-diamine. That sounds more correct. Okay. Anyway, this next one is butane 1,4-dioic acid. that was given in the previous question anyway. Butane 1,4-dioic acid. Let me check, did I spell that correctly? Yep, there's butane dioic acid. So yeah, I mean there's step 2, there's step 4, and then that is step 1 to make G, there is step 3 to make H. Draw the structure of G and H. Okay, now if we look at these, there's 1, 2, 3, and 4 carbon, and I have 1, 2, 3, and 4 carbon there. So we can definitely see that there's the same number of carbon there, so there's no additional carbon. But from the 4 carbon there, you can hopefully see that the original carbon there will be the middle carbon there, because then you have additional carbon, 1 at the end there, carbon 1, and 1 at the carbon 6 there, which I have drawn in blue. Not too sure, actually I've used a laser pointer to guide you here, rather than just to use the highlighter to put it in just now. But anyway, so you have added carbon there, you've added a carbon there. So the idea really there is add carbon. No need to add carbon. Okay, so we should be able to go backward in terms of which step require adding carbon, which step require not adding carbon. So if I'm to draw the structure, they don't say draw skeletal or draw structural. I personally would just draw skeletal, okay, because well, you know me, I like skeletal. So that is just going to be butane 1,4-diol. That's just going to be G there. So that makes sense for G, because we could just do hydrolysis. So this is going to be hydrolysis, is the type of reaction where you're actually substituting the Br with the OH. And then what we can do with that OH at the end there is we could oxidize a primary alcohol to carboxylic acid. Primary alcohol because the carbon with the OH is bonded to one carbon. Primary alcohol because the carbon with the OH is bonded to one other carbon there. So this is just going to be oxidation of primary alcohol there. On the other hand, for H, we have seen that we need to add carbon. So this has to be done using nitrile. So there's C triple bond N, there's C triple bond N. So let me just get this straight. 1, 2, nope, I have done this incorrectly. Carbon 1 is still carbon 1 there. So it is carbon 1 that is bonded to a new carbon there, which is C triple bond N. It is carbon 4 that is now bonded to a new carbon. There's now triple bond N. So even if you want to draw skeletal formula, make sure that you are drawing the right stuff and not just randomly drawing without checking. So that is one of the biggest mistakes you can ever make, drawing without checking. So now I have 1, 2, 3, 4, which are the one in red. So obviously you don't use highlighter in the real exam, but I'm just showing you that the one in red and now the one in blue comes from this C triple bond N and C triple bond N, and that reaction there will be hydrolysis. So it's going to be the acid, oops, sorry, not acid, it has to be base hydrolysis. Am I correct? Nope, it's not hydrolysis at all, because hydrolysis would give you carboxylic acid. You want amine. So this is going to be reduction. You need to have reduction of the nitrile, then you can get amine. Cannot be hydrolysis, because then you get carboxylic acid. From here to here, that is definitely a substitution. The mechanism is called nucleophilic substitution, but the type of reaction is just substitution there. Okay, so I've done the structure of G and H. Now we need to think about reagent and condition for each of these steps. So step 1 is hydrolysis. I would need NaOH aqueous, because it is done in water. That's why it's hydrolysis. They want the condition. I will also need reflux for step 1. For step 2, this is the oxidation of primary alcohol. So I would need H plus and Cr2 or 7,2 minus. This is called acidified dichromate 6. And I also need a reflux condition. For step 3, nucleophilic substitution with Cn minus. So what I need is KCN or NaCN in ethanol, and I would need to reflux this reaction mixture. Okay. For reaction 4, this is reduction of nitrile to amine. So step 4, reduction of the nitrile to amine, I need lithium aluminium hydride, and this is to be used in dry ether, as lithium aluminium hydride is very sensitive to water, so we always use it in dry ether, and we can reflux this as well. Okay, so altogether, I will just copy paste each of these now, so that they are neat and tidy at the bottom there. I don't want that box there. Step 2. I'm just putting them all in one place now so that it's easy for me to find it and retrieve this file later on if I have to share with a student in the future. Of course, I am not sharing these online randomly. So I do offer private tutoring as well, so it's a $40 an hour. Everything about whether it's worth it or not, I can assure you it is definitely worth it given my expertise, given what you can learn from me on a one-to-one tutoring. Anyway, so those are the reagents and conditions for each of the steps that I have outlined previously. Going to the last part of this question is actually about polymerization for 2 marks. They say you can get polyamide, so polyamide L, and you get it from J, which is the carboxylic acid, HO, CO2H there, and you get CH2, CH2, and then CO2H, and then you have K, which is the diamine. So you're gonna form 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and then NH2, 1, 2, 3, 4, 5, 6. Okay, so this is your diamine. Oops, sorry. This is your diamine. This is your dicarboxylic acid. You want a polyamide. So you got to think about what will the OH lose. The OH will lose the, well, I mean the carboxylic acid will lose the OH. And then what would the amine lose? The amine will also, it will lose the H only. So ultimately, what you get is, you get the polymer. They want you to fully display the functional group. In the question, they say fully display any functional group. So the functional group that you're going to get is the amide. Amide functional group is going to be C double bond O and H like that. Even the O level or the IGCSE level education will have taught you that. So be very careful about that. So there's carbon O, and then there's your NH, and then there's your CH2, which I can just write, there are 6 of them. I think I should write using the simplified format to avoid writing so much. So there's CH2 there, because there's 2 CH2 as given in the question. And then of course that is also continuing to the C double bond O display there. There's the display of the amide unit, and the CH2 is also then combined to another NH, and that continues on and on. So this is polymer L, and I have fully displayed the amide unit. So that is going to be amide unit, and how many, or the amide linkage, they say draw the repeat unit. So this is the repeat unit, which consists of 2 different monomers, because each of the monomer has the dioic acid as well as the diamine group. So I need at least 2 of these monomer to condense together. This is a condensation polymer, because you are forming polyamide. This is condensation polymerization. Just like when you form ester or when you form amide, you kick out water. That's why we kick out the H and the OH there. We kick out water. It's a condensation reaction. So this is 1 repeat unit of this polyamide there. Fully display the amide unit. I have gotten the CH2 twice for the butane dioic acid there. I've gotten the CH2 6 times for the hexa 1,6-diamine there. And I think that's it for that 18 mark question number 6 there. Question number 7 is more organic chemistry synthesis. So they started out by talking about methyl benzene. So it's just 1 CH3 on the methyl benzene. And then step 1, they go to M. We don't know what is M. They go to N. We don't know what is N. And then they go to step 3. Step 3, we get this thing which looks a bit different, CO2H there, and then we get a NH2 there. So something has clearly changed. We need to think about working backward. From here to here, we have seen the CH3 there becomes CO2H. So we can think about oxidation of alkyl side chain. But the order of doing things is very, very important, because as stated in your data booklet, if this is CH3, a CH3 or any alkyl group is 2,4,6 directing. And if you have a CO2H group, it is a 3,5 directing. So we look at where we are here. If we direct from here, then our substitution will be here. here and here in green, whereas here we can see that these are not our green position, because if this is position 1, this is 2 and 3, so this is 3 directing. So we can see that if I draw that color, this is in position 3 relative to the CO2H. So meaning to say, if I do my NO2, which is my nitration, and then reduction, that means I will direct it onto position 3 and 5 if I have CO2H, but the NO2 will go onto 2, 4, and 6 if I have got a CH3 to begin with. I want it here, so I think I will do my oxidation first. So that means M is going to be CO2H, just like that. I think there's going to be M there. Okay, let me just put it in a bracket. Well, I mean a box, not bracket. I don't know why I keep on saying bracket throughout this tutorial. Anyway, so now the CO2H will direct onto position, if that is position 1, then it will direct substitution to position 3 and position 5, which is what we are hoping for. So this is going to be your nitration. So your nitration comes second and not goes first, because if nitration happened here, it will go to 2, 4, and 6. So decision really matter. So this is going to be N. And when you have nitration, that box doesn't look so good. That box looks better. So this is your nitration product there, and then from there to there you can just do reduction of the nitro group and you can get the phenylamine. Draw the structure of M and N. I have just done that. I have identified the type of reactions. So for part 2, step 1, what is your reagent and condition? I'm going to oxidize the alkyl side chain there. So our reagent and condition has to be the acidified KMnO4 or acidified MnO4 minus, and then you have to reflux that as well. Step 2 is your nitration. So nitration of a benzene group, that means it's a highly deactivated group. As this is not phenol, as this is not phenylamine, I cannot just use dilute nitric acid, it will not work. I need fairly extreme condition. I need concentrated sulfuric acid. I also need concentrated nitric acid. You should have learned how to write the balance equation to show the production of the NO2 plus electrophile. It's one of those things that they like to ask you in this kind of topic. And of course, I need to reflux that as well. And the reflux temperature usually is around 60 or 50 degrees Celsius. Very particular for this thing. What happened then is reduction. So step 3 is reduction. So reduction of the nitro group is very particular as well. So it can't use the normal reducing agent. Reduction of the nitro group require the use of tint and also concentrated HCl. And you also reflux this. By right, if you want to get phenylamine, if you do it acid reflux, you're gonna get the protonated version. That's why some textbook or some marking scheme, they will say after this reaction, then you would add NaOH in excess, because you want to get back the phenylamine. Otherwise it will get protonated to give you the salt with the NH3 plus and the Cl minus as the phenylammonium salt. However, I think most of the time in Cambridge exams, it's very rare that I expect this from you, but you should be aware that this is acidic conditions and this is weakly basic, but it is still basic. Okay, so this is just one of those things that I can add in order to make my answer as fully as possible, because I want to get the free base. I don't want the protonated base after all. In the next part of this question, part B, so we are told something about serine and lysine. So if we have serine, we have HOCH2. I think it's best if I just draw it in the normal way we draw amino acid, which is like this, H2N and then CO2H, and then we have CH2OH like that. So if you total the number of carbons, so they are, I mean, you can have a look at the structural formula given. So CH2, CH, NH2 twice. Nope, sorry, NH2 just on its own. There's 3 carbon, and then there is 1, 2, 3, 4, 5, 6, 7 of hydrogen, and there's 3 oxygen, and there's 1 nitrogen. And now you have lysine. Lysine there, if I draw the normal way I draw my carboxylic acid. What's wrong with my pencil actually? that, going to that, and then I have CH2, 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 and then NH2. So I have 4 of this CH2 as my side chain. So H2N, H2N, CH2, 4, CH, NH2, CO2H. So if you total the number of carbon, there's 4 carbon there, 5 and 6, so there's 6 carbon. Hydrogen, there's 2 and there's 8, so there's 10, 11, 12, 13, 14. So there's 14 hydrogen altogether. There's 2 oxygen and there's 1 nitrogen. Don't know why my hydrogen is appearing a bit dodgy there. If you read this question carefully, this part 1, what do they want? They want 2 structural isomers that could be present in the product mixture. So you have product mixture, but be very careful about reading the molecular formula, C6H12N2O5. C6H12N2O5. Looking at that, so 6 plus 6 will give you 12. This is molecular formula, which is already the actual number of atoms, so cannot be 6 plus 6. 6 plus 3 will give you 9, which is more than 6. The only way you can get 6 will be 3 plus 3. So we are looking at serine plus serine. But then, if I am just looking at condensation between the H2N and the CO2H, then I'll just get one product. Am I correct? Let me see. Usually when we condense them together, when we do condensation, C3H7O3N, if I add another C3H7O3N, if I total the number of carbon is 6, if I total the number of hydrogen is 14, and then O6 and then N2, I need to take out H2O because it's a condensation reaction. So if I take out H2O, so I can cross out 14, become 12. If I take out another oxygen, O become 5. So that is how I get one H2O and one of these. So I need to do one-time condensation. The question is, what do I do here? One-time condensation. Well, what are the 2 possible products? You must show the 2 functional group. So display functional group. I can see that you can get amide because this H2N and the CO2H can condense together. It could give you a dipeptide. So serine and serine. So you could get C double bond O and H like that. So there is your amide, or there is your peptide, and then there's your carbon there and your carbon. So looking at that, there is a carbon, it's got a CH2OH. So that carbon there, let me see, if I draw skeletal there, the carbon there has got CH2OH, the carbon there has got CH2OH, and I've got CO2, nope, not CO2H, but NH2 on that side. So it uses a CO2H on the other side to condense with another NH2 on that side. So this side cannot be NH2, but it is a CO2H. If you work out the molecular formula of these, you would definitely get C6H12O5N2 because I've kicked out a hydrogen from the NH2, I've kicked out the OH from the carboxylic acid. Kicking out one water will give me one-time condensation of these 2 things which are the same monomer coming together to give me this product after one condensation. The other product could be an ester. As you can imagine, you have an OH, you have a carboxylic acid. So if I have one of these, and I can draw like this, and then another one of these on here. So you can imagine that you lose the OH and lose the H there, such that your product is going to be an ester. So if I draw an ester first, C double bond O and O, and there's going to be ester there. So if I draw my amino acid first of all, so this thing is going to look exactly the same. I use the carboxylic acid, loses the OH, and now I have the oxygen from the alcohol, okay, because it loses the H, and this is bonded to the carboxylic acid as well as the NH2. So that is your NH2 and CO2H, your amino acid. It's got a CH2OH that now condenses with the carboxylic acid from this particular amino acid, which has got CH2OH, NH2, and the original CO2H there. Okay, so I hope that makes sense there. That is your ester functional group there. Okay, so I have fully displayed my ester functional group there. I don't want to break my ester functional group, so I'll just draw it like that. I just need to fully display at the ester as well as at the amide functional group, so I think I'm okay there. Next up, what do they want? It's 1 mark for predicting. Okay, so this is B part 2. Now I have C9, H19, N3 and O4. If I have C9, it must be 6 carbon plus 3 carbon. Remember just now, 6 carbon, and this is 3 carbon. So the 3 carbon was serine, and the lysine was 6 carbon. Serine was 3 carbon, lysine was 6 carbon. So remember, you could go from N to C terminus. So meaning to say, don't know why they keep on doing that. So N to C terminus in a way that, H2N there and CO2H there. So what we could have, let's see, we could have a lysine, serine. We could have a serine and lysine. So that should give us 2 possibility there. However, they're asking for the possibility. So you could have carbon to nitrogen terminus, meaning to say we would draw with CO2H there first, and then we'll have NH2 going that way. Again, we can have lys and then serine, or we can have serine and then lysine. So these are the 4 possibilities. As you could see, if you draw them out individually, then N to C terminus is different from C to N terminus. This is the usually accepted convention by biochemistry community. It's not saying that this doesn't exist, because this question is predict the number of possible different structural isomers. So there are 4 structural isomers that are possible altogether as a result of this combination, the ly going from N to C, C to N, but obviously 9 carbon is a combination of 6 and also 3 carbon there. Part C, so we have this, we have this big molecule. So if I just draw them out very quickly, so skeletal formula, I can easily draw them very, very quickly because it's just the beauty of skeletal formula. Is so that people can draw them easily without having to think about a lot of things to begin with. Okay, now we need to label each chiral center. So chiral center mean a carbon bonded to 4 different groups. These are formed from, this got a couple of chiral center. I can show you where it is. There's one there, which is chiral there, and there is another one there, which is chiral, and there's no chiral center there because this is a CH2, because carbon from 4 bond, so there's 2 hydrogen there. They say label each chiral center with an asterisk, not with a circle. I've labeled with an asterisk there. No chiral center there because CH2 and CH2. No chiral center on this carbonyl carbon because they are not bonded to 4 different things. Now you have complete acid hydrolysis. When you have acid hydrolysis, then your amide will break. Your amide will break. Let me show you if I just copy paste that, because I don't want to destroy that diagram. If I just remove that chiral center first of all. So you have an amide there and you have an amide there. So I'm going to break there and I will break here. So what that will give me is H2N, CO2H like that. And what this middle bit will give me is H2N and then CO2H like that. What that last bit will give me is HO2C, or I can draw the skeletal formula. And then there's NH2 that will give me CO2H. So what is different is this amino acid hasn't used this carboxylic acid on the main carbon there. Instead, it has used the carboxylic acid on the side chain in order to form amide with this particular H2N there. So what can we say? Oh, I just remember one thing. I think I've made a mistake here. I think I made a mistake here, because this is something with the NH2 on the side group. I just remember it. This is something with the NH2 on the side group. So we are still looking at nitrogen to carbon terminus. Carbon to nitrogen is not allowed. Okay, so we are still looking at that. But this is nitrogen to carbon terminus using side chain, using NH2 on the side chain. So I think it's very important that, you know, I go back and correct this thing. So I beg your pardon. So it is still 4 structural isomers. I just remember that when you have extra side chain, then this thing can also form amide with your other group. So it's still something from lysine to serine, something from serine to lysine, but this is using the NH2 on your side chain instead. Okay, so I hope that makes sense there with that correction there. So I will just very quickly move forward and back to this question. Okay, so back to this question, because this reminded me it can use the other extra CO2H to form an amide with the H2N there. So what we have there, we have draw structure of 3 products formed after complete acid hydrolysis. I have just drawn the 3 products. Okay, however, we need to consider the fact that we are in acid hydrolysis. So that means this is a basic group. So that means you will not get NH2, but instead you get NH3 plus, okay, because you are in acid hydrolysis. Acid hydrolysis means at the end of the reaction, all your basic group, all your alkaline group is going to be protonated. So there's going to be H3 and plus there. We are not told on what is the acid used, so I can't tell you the counter anion, but the nitrogen bonded to 4 different groups. I mean, nitrogen bonded to having 4 covalent bonds is going to be plus charge, just like ammonium ion there. Okay. Last but not least, onto the last part of this question, part 3. By referring to the structure of glutathione, why is it soluble in water? So if we look at the structure of glutathione, it has got the OH, it's got the OH, so these groups there can form hydrogen bond with water, and therefore it makes it soluble in water. So is it gluca or gluta? Glutathione has 2 hydroxyl group, has 2 OH, and how many NH group does it have? NH2 that can also form hydrogen bond, not the amide, but this one, the amide can form hydrogen bond as well there. So the NH2 there. This nitrogen, the lone pair is actually delocalized through the pi system, so it's not exactly available. So this NH2 definitely can form hydrogen bond as well. And one NH of the amine side chain, they can form strong hydrogen bond with water molecule. So if they can form strong hydrogen bond with water molecules, it makes them soluble in water. Therefore, make them soluble. Can't even write that properly. Make them soluble in water. So that marks the end of that. How many marks is that? 13 mark question. And we're ready to move on to the next question. Phew. This is question number 8. So this is an acid-base equilibria question. They have provided us a graph of pH against the volume of sodium hydroxide added. So we started out from an acidic pH, so which is around pH 3 if you read the graph carefully, and then it goes up like this, and then it goes up, and then it goes up like that. So there is an equivalence point there, so they have labeled that as equivalence point, and there is a certain volume which is not given there. I assume it's a calculation question. There is a slightly flattened line there. There is actually the buffer region, and if you look carefully, the equivalence point is roughly at pH 8, which is just above the pH 7 for neutral pH. If I look also carefully at where this thing particular end up at, that is around pH, give or take, around pH 11, pH 12, like that. So yeah, what we could say is this is starting out from a strong Is it from a strong acid? Strong, weak acid, something like that. Let me think. I don't know why I didn't think about reading the question. The question says ethanoic acid, so we know that ethanoic acid is a weak acid, and then we have sodium hydroxide, which is a strong base. So this is a weak acid and a strong base titration. So weak acid, strong base titration. You see, sometimes when you try to do something, your brain just goes totally blank. Anyway, so in the region circled on this graph as the first part of this question, identify the two organic species that are present in the solution. As you started out with carboxylic acid, of course you know the carboxylic acid dissociates to give you the conjugate base as well as the H plus ion in solution. And of course then in the middle of the reaction, as you add in sodium hydroxide, you are doing an acid and base titration. So this is going to be a neutralization reaction. They'll give you CH3, CO2 minus, Na plus H2O. What actually happened there is this is an acid-base neutralization reaction. So as this reaction goes along, this is continuously being produced in the same solution. Produced in the solution, but you still have ethanoic acid in the solution, so you still have this thing and this thing in equilibrium because you haven't reached the end point yet. So you still have the carboxylic acid as well as the you have the CH3CO2H and you have CH3CO2 minus Na plus. You have a weak acid and you have the salt of the weak acid. So this is essentially what you call a acidic buffer. So this is what you call an acid buffer or acidic buffer. You have a weak acid as well as the salt of the weak acid. So the two species present as required will be the CH3CO2H, which is the ethanoic acid, and you also have the salt, which is CH3CO2 minus, Na plus, as a result of a little bit of neutralization having taken place. What do they want? Explain the pH, why it only changes slowly and gradually. So the second part of this equation is basically give two equations to show why this buffer works. You know how buffer questions are usually very popular, explain or show by using two equations. What happened when you add a little bit of acid, when you add a little bit of base. This is essentially what is going on. These two are the active ingredient in the buffer. So what happened is this is the buffer region. This is the acidic buffer region, meaning the circle region. And this will resist or it will oppose changes in pH. Meaning to say, therefore, pH remains roughly constant. Roughly meaning they like to just stay the way they are. When a little bit of acid or when a little bit of alkali or base is added to it. Okay, acid or base, acid or alkali is added to it. And they give us 3 marks because we are supposed to write two equations. As you will know if you have done quite a lot of past papers, this is just a different way of asking this question. So H plus, if you add in H plus, which one in the buffer? Which of these will take away the H plus? The acid doesn't take away the H plus, it is the salt that will react with the H plus. So the salt is present in the reaction mixture, the buffer reaction mixture. So this is from the buffer, and they will remove the H plus added by forming CH3CO2H plus Na plus. And think about it, this is from the buffer, it removes the H plus and it forms something else which is already present in the buffer. That's why the pH remains roughly constant, because you're producing something which is already one of the two components present in this acidic buffer. On the other hand, if you have OH minus, if you add in a little bit of base or alkali, which one of these two will react and take away the OH minus? This thing is negatively charged, it's not going to react with the OH minus. In fact, it is the acid that will react with the OH minus, which is the base. So they will react with that acid, and that acid is present in the buffer. As the buffer contains two things in it, it's a two-component system. The base react with the acid to give you water, and in doing so, you will kick out CH3CO2 minus. These things are balanced in terms of atoms. These things are also balanced in terms of charges. So OH minus take away H plus, and you're left with the conjugate base CH3CO2 minus. And guess what? This is the other substance present in the buffer. As this is the other thing present in the buffer, you're not creating something new, you're just making something which is already present in your two component system. Okay, so that's how the pH remain roughly constant, because something from the buffer will react with the H plus or the OH minus that you add in order to give you the other substance present in the buffer. So this is still question 8. Question 8A part 2. So they're giving us a lot of 4 lines for 1 mark. This is quite extraordinary. So they're saying that you add in the acid and the base in equal proportion, but why is this equivalence point greater than 7? I mentioned about this briefly at the start of this particular question. You can think about it in terms of what you are adding. You are adding sodium hydroxide, which is a strong base, to a carboxylic acid, which is a weak acid. So when you think about it, strong base and the weak acid, you always, when you have mixed in the equal amount, the weak base dissociate partially to H plus, so the strong base dissociates completely into the OH minus. You're gonna have the OH minus overpowering the amount of acid when we think about equilibrium here, whereas this is not an equilibrium. So that's why when you mix this weak acid and strong base, the equivalence point is just above pH 7. On the other hand, if you have a strong acid and a weak base, it's also similar argument, and your equivalence point will just be below pH 7. If you have a strong acid and a strong base, your equivalence point will be somewhere in the middle, which is much closer to pH 7. So I think we are looking at this idea, the argument of ethanoic acid is a weak acid, NaOH is a strong base, so we're looking at a weak acid and a strong base reaction. So I can just state the obvious. CH3CO2H is a weak acid. It dissociates partially into H plus ion. It dissociates partially or reversibly, or it ionizes partially into H plus ion in water. And NaOH is a strong base. It ionizes, or it dissociates, whichever word you like, completely into OH minus. As a result of it, so this is a strong base, weak acid titration. So as a result of it, your equivalence point when you mix in this and this in equal amount is going to give you equivalence point just above 7, because the hydroxide will overpower the amount of H plus present as a result of this equilibrium dissociation. Don't know why they give 4 lines for that thing there. Question 8, part B, is a calculation question. They have 1 whole page, is a 3-mark calculation question. What we have here is we have ammonium vanadate. Let's see what's going on. So if I have NH4 VO3, this is 0.150 gram. So all of this solid dissolve in acid. What I get then is I get a solution. I get VO2 plus ions, and then I can add zinc to it. When I add zinc to it, zinc is a reducing agent, so the zinc itself will be oxidized and it will reduce the VO2 plus. It will make the VO2 plus gain electron as per the half equation shown, and then you will get V2 plus there. And you will remove the zinc by filtering any remaining zinc powder, because the zinc that go in the solution will be zinc 2 plus. You're going to do titration of this resulting solution. You're going to titrate vanadium 2 plus back to vanadium, what is this oxidation state here? Plus 1 is the overall oxidation state, equal to vanadium plus 2 times minus 2. So vanadium is plus 1, plus 4, vanadium is plus 5 there. This is vanadium plus 2. We're going to do titration with this vanadium plus 2 using MnO4 minus acidified. So there is manganese plus 7. The manganese plus 7 will go to manganese plus 2 in your Mn2 plus. The equation is given. On the other hand, what will happen to the vanadium 2 plus is that the vanadium 2 plus will go back to VO2 plus, which is the reverse equation based on the first line of the equation they've given you. So this is back to vanadium plus 5. So let's work backward. So this is the idea of backward titration. So I'm going to start off by talking about vanadium 2 plus 2H2O. I'm going to VO2 plus 4H plus 3 electrons. I've just reversed this equation as they have given us because we're going to oxidize the vanadium 2 plus back to the vanadium 5 plus. And I have been given this MnO4 minus plus 8H plus 5 electrons, giving you Mn2 plus 4H2O. We need a balanced equation to do stoichiometric calculation. You can hopefully see 3 electrons and 5 electrons there. You need a lowest common multiple called LCM, primary school mathematics. 3 and 5, you're gonna get LCM of 3 times 5, which is 15. So I need to multiply this equation by 5. I need to multiply this equation by 3, and then I add them up together. The question is, do I want to add them up together? Okay, maybe I add them up together first. I will have 5 times 2, which is 10H2O on the left. I will have 4 times 3, which is 12H2O on the right. So 10H2O on the left, 12H2O on the right will give me a net balance of 12 minus 10, which is 2H2O on the right hand side. So I'll get 2H2O on the right hand side. I will get 5 VO2 plus on the right hand side as well. I will get 3 Mn2 plus on the right hand side as well. How about the H plus? The H plus, I would have 20H plus because 5 times 4 is 20H plus on the right. I'll get 15H plus on the, 24H plus on the left, 24H plus, 20H plus, so give me 4H plus on the left hand side. So 4H plus. And what else do I have? My electrons will cancel out and I'll get 3 MnO4 minus. And I think that equation should be balanced out very nicely. 5 vanadium, 12 oxygen, because 3 times 4 is 12 oxygen. 5 times 2 is 10, 10 plus 2 is 12 oxygen, okay? 3 manganese, 4 hydrogen, internal charges, plus 2 times 5 is plus 10, plus 4, so it's plus 14. There is minus 3, plus 14 minus 3 is plus 8, is it? Plus 10, plus 4 is plus 14, minus 3, plus 11, okay? This is plus 5, and this is plus 2 times 3 is plus 6, plus 6 plus 5, well, plus 6 plus 5 give me plus 11. This equation is balanced because we started from something which was balanced, and all we did was we did the correct multiple based on lowest common multiple. Anyway, so what do we know? We know that this is impure, okay? This is impure. What is the pure stuff? The pure stuff is the VO3 minus, since this is NH4 plus. How much VO3 minus is in here? But this VO3 minus in H plus is going to be the same as VO2 plus. Therefore, the mole of the VO3 minus, or rather the mole of the NH4 plus, is equal to the mole of the VO2 plus, because I am just adding acid. So the mole is the same, okay? And you could imagine that because this is VO3 minus, is also vanadium plus 5. Since it's minus 1 equal to vanadium plus 3 times minus 2, the vanadium is plus 5 in there. It's just in acid, it changes to a different form, but it's still vanadium plus 5. What else can I say? What else can I say? Let's do the titration calculation now. Step 1. So I have the amount of these, and I want to know the mole of the vanadium 2 plus. Okay. Do I want to know the mole of the vanadium 2 plus? Let's see. Nope, not really, because the vanadium 2 plus come from the vanadium. Well, this is vanadium 5 plus to begin with. So it is this one that reacts with zinc to reduce it back to this. So however this much is, we'll give you that. So we're looking at the mole of the VO2 plus instead of the vanadium 2 plus. This is our reactant, but this was obtained by reducing this with zinc. So the mole of the VO2 plus is to the mole of the manganate 7. 5 is to 3. This is how I set up my mole balance ratio from the balance equation. Okay, so label, and then from the balance equation, and then what is the actual amount? This is the actual amount of the mole, and then at the bottom is going to be my value. So convert cm cubed to dm cubed by multiplying by 10 to the minus 3. That means divide by 1000. And then mole equal to concentration times volume. This is mole, this is mole. Everything is to do with mole. The top bit is reserved for this based on what I label. If you have got the label the other way around, doesn't matter. This would be the other way around, this would be the other way around. So the mole of the VO2 plus, actual mole, bring that up. So there's going to be 5/3 multiplied by 20.10 times 10 to the minus 3 times 0.0250. And I got my calculator at 0.375 times 10 to the power minus 4 mole. This much mole, this will give you that in your reduction. So the amount of this is equal to the amount of this present here. So what we have is the amount of this here is the same as the amount of the ammonium vanadate 5 there. So the amount here is the same as the amount here, which is the same as the amount of this, the reactor with the MnO4 minus. So what I can say is the mole of the ammonium vanadate is going to be the same as the mole of the VO2 plus that I obtained when I dissolve this in excess acid. I want to know the mass of this. So on the left hand side, I'll have mass over the MR, which means I need the MR of ammonium vanadate. So straight onto the, it is given 116.9. So 116.9, that will give me mass over MR, which is the mole of that solid, is equal to this much mole from the reaction. So there's 8.375 times 10 to the power minus 4 mole. Bring that up. So that was our previous answer, multiplied by 116.9. That gave me a very long list here, but I will just round it up. So 0.097904, because the next number is 375, so I will just round it up there. This is not my final answer. This means out of the 0.150 gram, which was impure, only this much is the percentage of NH4VO3. So it's 0.097904 gram divided by your original mass, which was the impure sample, times 100%. So what you have now is gram and gram cancel out. So that previous answer divided by 0.150 times 100, I get 65.269. They want the final answer to 3 significant figure. So I look at the next number. Oops, sorry. I don't know why that. Hang on. Yep, okay. So this is the number next to the 3 significant figure. So this is more than 5. So I need to add 1 there, which gives me 65.3%. And this is to 3 significant figure there. That's the end of that 7-mark question. And question 9, so this paper just keep on going and going and going. Question 9 is about carbon-13 NMR. So carbon-13 NMR, this is for compound A, which is C8H8O2. Better write that properly, otherwise I might not be able to read my own handwriting. There are 6 peaks. So there are 8 carbon, but 6 peaks. So that means there's a bit of symmetry there that we need to keep an eye out for, because by right 8 carbon would mean if all 8 are different, I should get 8 peaks, I get 6 peaks, meaning that some of them are chemically equivalent. Now what can I say here? There's no question here, it's just, I don't know why there's no total for this question, because it's just 6 marks for this 1 page, and that's the end of the paper actually. Oh well, never mind. So what else do we know? Information. A reacts with bromine water. Bromine water means aqueous bromine, and you get B which is C8H6 Br2O2. So A previously was C8H8O2. You can hopefully see that this is addition. This is an addition because 2 things become just 1 thing. The number of carbon, it remains the same. The number of hydrogen has the number of hydrogen has decreased actually. Wonder why. The number of hydrogen has decreased. The number of oxygen is the same. The number of oxygen is the same. The number of hydrogen decreases. So you have replaced or you have substituted 2 times hydrogen for 2 times bromine. So I was wrong. This cannot be addition. This must be substitution based on my discovery that the number of hydrogen gets down. So you decrease in the number of hydrogen, which means we do kick out HBr. We kick out 2 HBr. This is a balance equation. This is your substitution reaction. This probably means it's going to have a benzene ring because this is going to be electrophilic substitution mechanism. This is not common of alkene chemistry. Not just any alkene, but this is going to suggest aromatic, meaning it has benzene ring. So benzene chemistry, not carbon-carbon alkene. At least that's my take from this first information here. So how about the second information given? The second information given is A reacts with alkaline aqueous iodine. Alkaline aqueous iodine is the test for iodoform. So A is C8H8O2. And what does that give you? They give you a yellow precipitate. So this yellow precipitate is the easy thing because this is triiodomethane. So triiodomethane is the positive result that come from the test, okay, the test of which it is positive test for CH3CHOH functional group or CH3C double bond O. So I need a bit of space there. CH3C double bond O. It's N or because this thing come in AS under alcohol topic, this thing come in AS under carbonyl topic. So going back to what I can say about D, so they haven't mentioned about D yet, but your carbon has to come from here because you are not adding carbon, you are chopping up, you are fragmenting the carbon from the main thing there. So it's got this or the other thing. What else can I say? So I can say that they must have this group or this group such that they will react with that. How about observation number 3? Compound D reacts with PCl5 and you get compound E, which is C7H5O2Cl. This is convert, or you get the alcohol. In fact, it's not just alcohol, it could also be carboxylic acid to basically convert the OH. Convert the OH of alcohol or carboxylic acid to Cl. So basically, if you have alcohol, then you will get halogenal alkane. If you get carboxylic acid, you get acyl chloride. Okay, but here you have 1 chlorine. So what does this tell you? So this is just single conversion. Single conversion would mean only 1 time OH in D. But this OH cannot be a phenol. It has to be either alcohol, which is not phenol, so it cannot be phenol because phenol doesn't do this reaction, or it could be carboxylic acid. At this stage, we can't tell much, but you can hopefully tell that 7 carbon. So I can work backward now. 7 carbon. Previously, I have 8 carbon. I cut away 1 carbon, so this is going to be 7 carbon because this information tell me that there are 7 carbon here in D, and that's very, very important. If I have to work backward, which is basically this line here in green, work backward. So remember, we are replacing 1 single OH with Cl. So what I'll do is I'll cut out. So D is going to be C7. I am, excuse me, I remove the Cl and I add in the OH. Then I'll have H6 because I have 1 extra hydrogen. And I will remove the OH just now, so I have O3. So D is going to be that because I removed the OH and replace it with Cl, so I remove 1 H. they give me 5. I remove one O, they give me 2, and then replace the OH with a Cl. So it's just one hydroxyl OH group, which could be carboxylic acid or alcohol. We don't know that at that stage. We just know that 7 carbon and 1 carbon, because that give me 8 carbon in A before I reacted it with alkaline aqueous iodine, which chop off 1 carbon as a result of the presence of either of these groups that actually give me this positive iodoform test. Anyway, so moving on to the observation number 4. What other information can I derive from this? E reacts with propane-2-ol. So what is propane-2-ol? Propane-2-ol is this, 1, 2, and 3. And I get this compound F. Is F given? F is not given. What do I know? I know E. I know E has this chlorine there, but it reacts with alcohol. Halogenal alkane does not react with alcohol. Halogenal alkane does not react with alcohol. RX halogenal alkane. No reaction with alcohol. No reaction with alcohol. So the fact that this thing reacts with alcohol and you have alcohol there, so most likely we are looking at condensation reaction. This condensation reaction between alcohol and something, condensation reaction means this F is going to be an ester containing C double bond or like this, and this implies that, so this brings back to the idea that E must contain acyl chloride and not a halogenal alkane, okay? Because if it's halogenal alkane with this, no reaction, so it must contain acyl chloride. If E contain acyl chloride, so if E contain acyl chloride, that means D, therefore D is a carboxylic acid, therefore D is carboxylic acid. So C point number 4, okay? So if E is acyl chloride, so therefore D is carboxylic acid. And D is carboxylic acid, and that makes sense from there, because when you cut through the alkaline aqueous iodine, you're going to end up with a carboxylic acid terminus. Actually, it's under alkaline condition. You do actually get the salt, but you do protonate it with excess water, and then it will give you the carboxylic acid there. What else? Now draw the structure of compound A, B, C, D, E, and F. Let's try. Okay, let's try. Now, looking at question 9 again, at the beginning we say C8H8O2. This really reminds me of there's a benzene ring, as we said just now, aromatic of benzene ring. So perhaps I can start by drawing a benzene ring. I cannot. Can I? Let me think. Can I have a OH? Maybe I have a OH, or maybe not. I have 8 carbon, so 8 carbon, but I have symmetry, so perhaps that is correct. Could be that, could be this, like that, symmetry. So let's work through it and see. This is 1, 2, 3, 4, 5. There are only 5 peaks there because there are 5 different carbons. But these are just carbons. These are not even the one with the oxygen. So I haven't dealt with the oxygen yet. I'm just looking at the carbon. So there's a symmetry there. These and these are different. These and these are the same. These and these are the same. So 1, 2, 3, 4, 5 cannot be these. This is a 1, 2, 3. There are only 3 peaks there. So cannot be that as well. So perhaps it's something like this. Not too sure really, not too sure. 1, 2, 3, well there's a symmetry down there. So 1, 2, 3, 4. We're looking for 6 peak. I think we can't really start from just this thing. We have to consider the O2 there as well. So, you know, those things are not going to be useful. I'm just going to rub them out. Okay, so let's try and think about this again. Okay, so we know we have benzene ring, definitely. We have benzene ring. We know we have this thing, which is this alcohol or this C double bond O. We know that this is carboxylic acid because it could go there. So now I have 7 carbon. And if there is 7 carbon, this D here must be 7 carbon as well. Which you said D is 7 carbon. And there is a benzene ring and there's a carboxylic acid. So this one has benzene ring, and then this one also have carboxylic acid. So that should give us our 7th carbon, because 6 carbon from the benzene ring and 1 carbon from the carboxylic acid. So there has to be 7 carbon there. So I can probably start from D. So let's see where I can start from. So we are going through analysis, right? So if I start from D, D just now was a 7 carbon carboxylic acid. So 7 carbon carboxylic acid. But what is the formula of D just now? So we work out from here. We could go backward, where we take away the Cl and we add in the OH, because the OH in D get replaced to give you this acyl chloride, as I said. So C7H6O3, C7H6O3, this should be D. Let's just double check. We have 6 carbon, 7 carbon. We have 5 hydrogen, plus 1 is 6 hydrogen. We have 2 oxygen, but here is 3 oxygen. We have 1 more oxygen, which cannot be there. And if we have 1 more oxygen, then it cannot be ester. It has to be alcohol. But the alcohol cannot be here, because this is carboxylic acid. So it's got to be a phenol. Okay, so it could be this, or it could be this, or it could be the other possibility where it could be that. So there are 3 possibilities here. So which one is D actually? We have to think about it. So all of these could be D, but I don't want to go here, because if I go here, it's the exact same thing as that. If I go here, it's the exact same thing as that. So it could be either of these 3 positioned. In terms of the position, I think that is where this information will come into play, which is the NMR peaks. So we have to try and work backward. So if I have D as one of the 3 possibility, and then I have A has C8H8O2, I need to try and put in, is it this group or is it this group? A is C8H8O2. A is going to be C8H8O2. Am I correct? C8H8O2. I have a positive iodoform test. So I have a positive iodoform test. So remember, when I have a positive iodoform test, I will cut off the CH3CO or the CH3CHOH. So it has to be the other thing. It has to be the carboxylic acid that actually give me the original group there. So perhaps I am looking at CH3CO like this, or could I be looking at CH3CHOH? So it depends on really which one are we looking at. Are we looking at CH3CO or are we looking at CH3CHOH? I don't want to draw for these and these first, because I just want to work out the identity of A first. Is it going to be this alcohol? Is it going to be this ketone here? So let's try and work out the molecular formula. So there is 6 carbon, 7 and 8. So this is C8H. There is 1, 2, 3, 4, and then there's 5. And then there is 3 hydrogen there, so there's 8 hydrogen, and there is 2 oxygen. So this is C8H8O2, which means this cannot be C8H8O2 because there's an additional H there, and there's additional H there. You can try and work it out. So C8, but then the hydrogen will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there will be 10 hydrogen and O2, so this is not A. So meaning to say it is not CH3CHOH, but it is a CH3C double bond O. So having said that, if that is the one that give me positive iodoform test, I then need to think about which isomer is that. So cannot be this, so it has to be this, but then I need to also decide if this is A could also be the other one where the OH is there, and then I have CH3CO like this. A could also be where the CH3CO is on this carbon here, and then the other OH is on that carbon. So all of these could be A, which is C8H10O2, so there's A. Alright, so now we have to use the NMR information. The NMR information told us that we have a bit of symmetry, but not a lot, because 8 carbon give me 6 peaks. 6 different carbon there, okay. So let's have a look at these options for A, where we work backward from there. So 6 different carbon. Hang on, I want that in green, I want that in red. 6 different carbon. So there's 1 carbon, 2 carbon, so I'm on this one at the moment. 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5, 6, 7, and 8. There are 8 different carbon there because there's not a lot of symmetry. So let me just show you for the other one. If I use a different color, so let's say I use pink. So 1, 2, 3, 4, 5, 6, 7, 8. There are also 8 carbon. So what in the world are we looking at? Okay, forget about it first. What about the next ones? Let me use a different color, brown color. So there's a plan of symmetry here. I hope you can see that there's a symmetry in between there. So definitely these and these are the same, and then the pink one and the pink one are the same, and then you have a blue one there. It's different from this black one here. So there's one, I should probably use a different color to show that much better. Orange one, for example. So you got 1, 2, 3, 4, and then 5 and 6. So you got another 5 and 6, 5, and you got another one which is 6 there. So there's no other carbon, so there's 1, 2, so these and these are the same, these and these are the same, 1, 2, 3, 4, 5, 6. So there's 6 different carbon. So we're looking from that NMR information, we're looking for something that has 6 carbon environments. This one has 1, 2, 3, 4, 5, 6, 7, 8. Remember, this one has 8 different carbon. I shouldn't have to count again based on what I have just done previously. So we know that it cannot be these. We know it cannot be these because these have 8 carbon environment for that compound A there, for that molecule A there, which also means that these cannot be your D, which means we are looking for this as being your A, and we're looking for this as being your D. Okay, so going to all that information, so I can just we can just start fresh, and let's have a look at your table again. So this is a 6-mark question. In ideal situation, you're probably not spending this much time actually, like going through all the thing that I've just mentioned, because you will be working a lot faster in the real thing, because all of these are just basically how to help people in general to try and understand the underlying analysis. This is the last question as well, so some students might even skip the very last question because they have no idea on what to do at all. This is C8H8O2. So we can now work forward. So this is your alkaline aqueous iodine. Ideally speaking, in an alkaline condition, you actually get carboxylate salt. So this is your yellow precipitate, which is C there. And then this is D, which I just talked to you about. Ideally speaking, if you are in a alkaline environment, not just the carboxylate there, but also the O of that hydroxide should be O minus, and then this one will be C double bond O minus, like that, because you are in alkaline environment. Phenol is weakly basic, weakly acidic, that's why it will be deprotonated by alkali, and this thing is a carboxylic acid that will be deprotonated by the alkali. But seeing how compound D can react with PCl5 in the later stage, I assume they do actually protonate this at the end, such that we are not expecting the carboxylate to be around. So we're just expecting D to just be the carboxylic acid, which we can then react with PCl5 to try and turn that into acyl chloride, like that. Don't forget your OH doesn't turn into halogen alkane because it's a phenol and not a normal alcohol. And of course that will react with your, that is E there, so that's C7H5O2Cl. That will react with propan-2-ol, which is an alcohol. The alcohol will react with the acyl chloride to give you an ester, not the alcohol on the benzene, so the phenol doesn't react, but that acyl chloride will lose the Cl, this will lose the H, so that will be combined with the O, and then you have the branch group there because it's propan-2-ol. This is your ester F there. going back to the original structure, we talk about the reaction with Br2. Actually, we haven't talked too much about the reaction of Br2, but you know this is definitely correct based on the amount of NMR peak. You know that with Br2, the OH directs to this position, which I've marked in blue, but this position in blue, this one is blocked because there's something there already. That is why it only results in 2 times substitution instead of 3 times substitution. So that is why your final product only has 2 bromine in it instead of 3 bromine, because the other ketone is still present. That's why B is C8 H6Br2O2, and we know this is a substitution because earlier on I did actually try and look at it. We saw there's a decrease in the number of hydrogen. If it is addition, there will be no decrease in the atoms. You're just adding Br2 onto the normal double bond, but this is electrophilic substitution on the benzene ring. Because you want to go back to being aromatic, you will substitute the hydrogen on the benzene ring with the Br as a result of very, very strong activating effect. So this is called activating effect of the phenol or the NH2 group, and they direct to position 1, 3, and 5 there. Okay, so there is B there, and I think we come to the end of this particular question. So I've got everything sorted out here: A, B, C, D, E, and F. And yeah, I mean, I explained through the whole questions in our analysis prior to actually showing you this stage here. Yeah, I hope that was useful. So don't forget to click the button on the bottom right to subscribe to the channel, and if you think this video is useful, so do leave a like for the video and share the channel widely with all your friends, chat group, juniors, seniors, and many other people. In time, more tutorials will come, but it does definitely take time to catch up to this kind of full paper video tutorial, especially in this restructured format where I don't show the question paper anymore as a result of copyright issues that Cambridge has with my previous videos. And don't forget to actually follow me as well at ptet.chemistry. There's at ptet.chemistry on Facebook, Instagram, and Twitter to get connected, send in messages and queries and whatever. Okay, so see you in the next tutorial video. Thank you for watching.